Now I am going to start the first session of the fourth day GIAN course on PV fuel cell microgrid, a sustainable energy solution. So in my today's lecture, I am going to continue the first part, means already which I had covered yesterday's in the yesterday's lecture, that is power management of PV battery supercapacitor hybrid energy storage system based microgrid. So first part I have covered. Basically yesterday, if you will see, I have talked about So in my today's lecture, I am going to cover the, yesterday as I have told, I have covered the PV wind based system having a single energy storage system, that is we have considered a battery energy storage system and its integration, its implementation and how power management takes place in a single system, single renewable energy system with a single storage. And then I have added another source to it and then explained the power management of it, means and how the complexity is increasing by adding one more source with a single storage. But today, as already mentioned, I am going to start with a single energy source with a hybrid energy storage system, and till now all of you are aware of what is the advantage of adding one more source, one more storage, okay, which is having the complementary characteristics like the battery and supercapacitor. And I will first show the one simulation, its implementation, then its power management, and same thing will be shown with the wind energy based system having the hybrid energy storage unit. And finally, I will explain both the source having two sources and two storages, that is hybrid energy
video
system.
Is not available, ma'am.
Yeah.
Your video is not available.
Video is not coming.
Yes,
ma'am. Please, okay. Now is it coming?
No.
No, ma'am.
Okay, just we are trying to solve it. What is the problem? Huh? Any problem there? Huh? No, why team it is not coming? Okay, it is available in YouTube, otherwise you can directly connect to the YouTube and see the live video. Okay. So can I continue? Are you able to check? Can I continue? These things you could have done much before, huh? Is it coming now? No. So can I continue, online participants? Please respond to me. Should I continue? Okay. So let us start. So as already I mentioned, I will first show the simulation and implementation of a PV based DC microgrid having hybrid energy storage system, then the wind-based microgrid having hybrid energy storage system, then the combination of both wind and PV having the hybrid energy storage system. And then I will conclude my today's presentation. So coming to the system we have considered, as already I told, this we are taking a system, PV based system. Okay, and here if you remember, you can recall, yesterday I have shown a PV system with a boost converter, but now I am showing a PV based system with a buck converter. What already I have mentioned, what type of converter we were choosing based on our bus, means what is the available output voltage of the PV and what is the DC bus voltage. So initially we have designed the system with a lower output voltage, so we have used a boost converter to boost it to meet the bus voltage at 48 volt, and this 48 volt. Okay, and so accordingly we have designed the boost converter. Yesterday's, if you will refer to the yesterday's slide, which I will be sharing soon. And now, because of our availability of the rooftop application that is available in our lab, so we have changed it to from we have again designed the system with a buck converter. Okay, so which is working in the MPPT mode, and we have added along with the battery. Now we have introduced this supercapacitor having a bidirectional converter. So now we have two storages having complementary characteristics and two bidirectional converters, which is interfaced in between the storage and the bus. Okay, so this configuration is called the active parallel active configuration. And what are the other configurations available, that I will address in tomorrow's tutorial. Just because many things I am focusing on the power management in today's lecture. After that I will talk about the MPP also after this lecture in the first tutorial. So first you just see I am having a single storage, single source and hybrid storage. Okay, yesterday I have explained, started with a wind energy system, now I am showing with a PV based system, and I have changed the converter also because of our system requirement. So accordingly the buck converter, the design of the converter, here we have not contributed anything. These are the standard converters design, which you can refer any paper, and I will also give the references. You can do the converter design accordingly. Already 2 times I have explained. So this buck converter can also be explained in the tutorial session. I will explain the detail of the design of the buck converter. But now I am just going to the next part of it, that is I'll just explain you about what is the change in the control part. When I am adding along with the battery with the bidirectional converter, which is regulating the bus voltage. Okay, so that already we have seen. We are having a dual loop control. Outer is the VDC control loop, inner is the battery current control loop. Okay, so the battery this VDC control loop giving the battery reference current. Okay, which is regulated or the charge discharge control of the battery is done in the by the inner current loop. Okay, so here, so this is the control we have used when we are going for a single storage system. But when I am hybridizing, okay, so the buck converter or the source renewable, I am not changing anything. So buck converter is operating in MPP mode. But when I am adding one more storage to it, and I am using a active parallel configuration, means two bidirectional converters are there, one for the battery and one for the supercapacitor. Okay, so that what is the role? So both of them are responsible to regulate this bus voltage. Means they are trying to keep it at 48 volt. So with the single also we are doing, but now I have added, but how we will change the control action. Okay. So you can directly also that what are the other configurations available. I will talk about that in the tomorrow's tutorial class. Just you see here we have used a very simple and very popular one. This is the filtration based HESS control technique, where we are using a low pass filter, where we are segregating the reference current generated by the outer VDC loop. Okay. So here also dual means inner outer voltage control loop, inner current control loop, but current control loop, one is for the battery current and the another is for the supercapacitor current. Okay. So where we are segregating the net reference current to the transient part and the that is the steady state part. So steady state part is the battery reference current. Okay, battery is responsible for the steady state operation and the transient operation like load change. If the PV system, it is the irradiance change, and if it is a wind system, it is a wind speed change. In those conditions, this supercapacitor is taking part of the role, and that how we will decide. Okay, inherently it can do without any control if you are doing, but it cannot be done in a optimized way or the proper way. Okay, so here exactly we are segregating. That's what I want to say here. In the control, what we are using when I am going for a hybrid energy storage system, there are many other control techniques also. This is the simplest one and oldest one. So we are going for this low pass filter based method where the outer this PI controller which is giving the net reference current here. Okay, this it is the output of the low pass filter is giving IB reference. Okay, IB means battery reference current, and I am subtracting this from the INet reference current minus the IB reference current is giving the supercapacitor reference current. Okay, so next is the two loops are the current control, inner current control loop will be designed accordingly to means we have segregated the reference commands we have generated, so that the transient component will be handled by the supercapacitor and the steady state component will be handled by just a minute this battery. Okay, so here actually I am having some problem in 1 minute. If you will see, this is the net reference current that is generated from the VDC reference loop or the VDC loop, and then this is the IB reference which is the output of the LPF I have shown here. Okay, again I am clearing it. So here if you can see it clearly, and then the supercapacitor reference current is we are getting from the INet reference minus the IB reference. Okay, and here the supercapacitor for the this LPF, the low pass filter, the cutoff frequency is chosen as 5 Hz. Okay, so here it is given in radian per second. Okay, 5 Hz is the cutoff frequency that is we are using here. So that how it will be affecting the operation directly I am not showing any other, because bidirectional converter design yesterday I have explained. So now we are going to with that, after that designing we are getting this is the PV configuration we have taken here for the simulation 1 kilowatt system. Okay, and we have tried to simulate the whole system, means buck converter operating in MPP mode and HESS is connected to it. Okay, and here what we will see, this is the buck converter design. The design will be shown later. Just values of each parameter is given here, and taking all these parameters into account, this is the battery as well as the supercapacitor pack. If you will see, you can mark here, yesterday I have shown a battery capacity of 36 volt. Okay, 3 12 volt batteries are connected in series, but now we have come to lesser than that, 2 batteries 42 ampere hour each, but the same configuration we are using for the experimental purpose also. And here the supercapacitor also we have taken, that is 16.2 volt, 2 are connected in series, that is, so overall that is individual it is 58 farad, so 2 are in series, so overall it is 29 farad. Okay, so this is the rating of the supercapacitor along with the corresponding bidirectional converter we are using, the input capacitance, the output capacitance. Okay, and the inductor is 0.5 millihenry. Okay, for both the case we are using that. So, and the switching frequency for all 3 converters we are using 10 kilohertz. And this system first simulated in MATLAB Simulink, then we have implemented using this DSpace 1103 digital controller. Okay. So if you will see, we have for the simulation case, just here we have taken 3 test simulation test conditions. One is PV, the 1 kilowatt system PV, okay, having HESS, okay, the bus voltage is 48 volt, and we are seeing the operation with a irradiation change. I am not showing the mainly focusing on the MPPT part. MPPT results will be discussed after this in the tutorial class in detail. Okay, so I am showing the whole this PV HESS based system, the operations during irradiation change, during the load change, and when there is no sun. Okay, so here one more thing I want to specify, that both the hybrid the energy storage systems are within the normal operating condition, means SOC are not either it is in a fully discharged condition or overcharged condition. So here we have changed the this between 40 to 90%. Okay, yesterday's class I have shown it is 50 and 90, upper limit is 90. Okay, so today we have just changed to the, because this is depending on the standard. This also people are showing with 30% the load threshold. Okay, so you can set your limit and accordingly you can work. Okay, so coming to the result. So after simulating this, okay, you can see here there is a first one is with the variation of irradiance. Okay, first initially the PV at the standard test condition with a full means 1000 watt per meter square and 25 degree centigrade, we are getting a PV power of 1 kilowatt. Okay, and at this 0.5 second the irradiance is changed. Okay, at 2 it is made half, means 500 watt per meter square, the irradiance is changed, and so the corresponding PV power is also decreased to half of it. So you can see 1000 watt to 500 watt. Okay, but you can visualize here the load power is maintained constant. Okay, that is 750 watt. So what is the difference? Yesterday also similar type of result I have shown, but the whole transient as well as the steady state component is supplied by, means when there is a sudden change. So sudden change in terms of the source, renewable energy source. So first I have shown for the battery case, and here previously both the components, so there is a peaky, the current of the battery is peaky in nature. Okay, so the size of the battery need to be higher than the this case when we are going for a hybrid energy storage system. If you see clearly the low pass component after the low pass filter, this is the battery power and it is also visible in the battery current. It is smooth. Okay, and whereas the transient component in all other cases during steady state operation the supercapacitor current is maintained at 0, but the high pass component or the transient component is clearly very nicely it is shifted to the supercapacitor. Okay, so there is a change, irradiance decrease, then there is a irradiance again increase. In both the cases it is managing well, if you will see. Okay, so the transient part is supplied by the in terms of current, if you will see, and so the battery current becomes smooth in nature. Okay, so it improves in long run, it improves the life of the battery. Okay, so that is the reason we are going for this, adding this hybrid energy storage system. So same thing, if you will see in both the cases for this during irradiance change, increase and decrease, first is decrease and increase condition, there is a we have what the VDC is, there is a drop in VDC and spike in VDC, both is maintained constant after certain interval. Means that means the controller is designed well so that it can be, it is tracking its reference value well. Okay, so this is the case, and correspondingly here the battery charging, discharging. So initially the excess power it is as the load demand is less compared to the generation, battery is charging. Okay. Then when there is a less, the PV power is decreased to 500 watt. So rest on energy is supplied by the battery. So in the current as well as it is clearly visible, and correspondingly also in the power. So it is negative means it is charging, battery is storing, and when it is there is deficit power, then battery is supplied. Okay. So all these waveforms, and this is actually another, this is the PV side voltage waveform, which is for the showing the MPP operation. Okay. It is maintained at VMPP. Okay. So this is the result when we are operating the system with a irradiance variation. Okay. Second is, in second case, we are doing with a load, there is a sudden change in load demand. Yesterday I have shown the wind system with a low power level, 100 watt, 175 watt, like that results. But here, as we are simulating, and we have gone up to 1 kilowatt, and corresponding the load, previous case, here you will see load power is 750 watt constant, but when we are going for the load change, the PV power is maintained constant at 700 watt with the corresponding irradiance, and here you just see the SOC of both the storage, that is battery and supercapacitor, is within the limit. Okay, 40 to 90 within that percent. So we are just operating, first we are testing under normal operating scenario. Okay, so we are not going for the battery protection mode. Okay, so in that case, so here when we are going for a load change, so what you can clearly see here, when we are going for a load change, load demand is increasing from 700 watt to 1 kilowatt, again it is decreasing to 400 watt. Okay. So in both the cases, PV power, PV generation is same. We are not changing the irradiance, means there is no change in the output of the PV system. Load is changing, output is, how it is possible? It should affect the variation in the load. For what is the reason why it is not affecting? Because the converter responsible for this, means drawing the power from PV, is operating at MPP. So any load change is not affecting, only irradiance change or temperature variation will affect the variation in case of PV based system. But load change, as your MPP algorithm is properly tuned, it will not affect, it will not give any disturbance on the PV output. Okay. So it will generate the same power, or it will operate at MPP point. Same thing I have shown for the wind based system yesterday. And if you see there, here also the VDC is for this load change condition also, increase in load, there is a dip in bus voltage, decrease in load demand, then there is a spike. Okay. Surge in the bus voltage. Okay. So correspondingly the current, for whether it is a load change, any transient. Okay. So what about we have seen in case of irradiance change also, the transient part is supplied by the supercapacitor. So battery current is very smooth, if you see. Okay. So and this is the charging condition and discharging condition, that is depending on to maintain the power balance. If you will see, we are getting, that is here we have one source PPB should be equal to the PHESS, okay, plus minus PHESS depending on the, and plus P load, and that is, if you will take in this side, means right side it is plus P loss, or the generation power minus the loss that is occurring in the system overall, means the converters, the PV system itself, the bidirectional converter, the battery, overall loss should be supplied to the load and the storage units. Okay. So this is the case when we have, means we are kept the irradiance constant and the load is varying. Third is the case when, means we are designing the system, it should be reliable, means during night time also it should be able to handle the load demand. So we have seen a condition when there is no sun, PPB is 0. Okay, if you will see, there is no PV power. Okay, PV generation is not there. So it is equivalent to a battery, means only HESS supplying a load. So in tomorrow's class, that demonstration we will see in the lab setup directly. Okay, that's just I am showing it is similar to, because there is no sun. Here I am showing a PV power is also shown here because system is integrated. Okay, so here same thing is again happening. So here there is no, means source change condition will not arise. There is no source. Okay, so only during with the load change 500 watt to 750 watt, again it is decreasing to 400 watt in both the cases. You just see supercapacitor how it is handling the transient clearly, and the battery is, so that's why giving no peak current, means it is only transient steady state part is provided by the battery, and correspondingly the DC bus voltage regulation is also happening. So if you see here I have shown all the reference currents, means the controller is designed so well that the battery reference current is tracked, means actual current is tracking the reference current. Similarly the supercapacitor reference current also is also tracking by the actual current is tracking the supercapacitor reference current, that is the transient part of it. Okay. So here IPV is also 0, here PPV is 0, so there is no sun. Okay. So this is the 3 cases we have simulated. Then we have tried to implement this system in our lab setup. Okay. So obviously initially when I have tried, we have done the simulation for 1 kilowatt system, we have means designed the system for 1 kilowatt, we have done the simulation for 1 kilowatt, but initially because of the availability and the battery rating what we have chosen 42 ampere hour, so we have tried for a lesser power operation. So here if you will see the PV, instead of the PV based system for which I have shown with the lamps, we have now we have a PV emulator. So we have replaced it by a PV emulator, so we can go for little high power. So with the lamp setup, that was irradiance is very less, so we were getting maximum of 34 means 40 within means less than 100 watt power. But now we have gone up to 500 watt. Okay, so this whole system, the sensor already I have told yesterday's class. Each in its battery pack, this is the supercapacitor pack which was not available yesterday because it was a single storage. Having yesterday you might have seen there are 3 batteries. Okay, here it is 2 batteries, so 24 volt. This is a supercapacitor cap, this pack having 16.2 volt each of 58 farad. They are also in series forming 29 farad supercapacitor, and these are the this is the buck converter. And there are 2 legs inside this box. Okay, this is the inductor of the battery and supercapacitor. This is the bidirectional converter 1 and 2 are inside this box. Okay, so now this system, after developing this system, it is we are trying to run it on using the DSpace DS1103 digital controller. So we have all the sensors which is here. Okay, inside it here some. This for the PV system, and here yesterday I have shown for the wind system. So this is means totally we have separated for one part for the PV, one part for the wind. Okay, so tomorrow you can see live this setup. Okay, and here this is a load we are going to change for checking this in the similar condition, means first varying the PV irradiance. Okay. So this after individual unit is tested, then we are integrating. It is not that totally I am showing means it is developed at one day. So each part, this PV with its converter is tested first, then the battery with its converter, then the supercapacitor, then whole system is integrated. Okay, the correspondingly the sensors are also tuned. So this is a complete implementation also takes a lot of time. So here this is the experimental results, which for this again for irradiance variation similar condition but at a lesser power level. Okay, we have done the whatever I have shown for simulation, that is 1 kilowatt 500 watt, but here we have done at a lesser load power, because here we have not used this whatever available rheostat we are having, we are able to get this amount of power. with this. Okay. So here the PV power is, we have operated it first at 500 watt, then the irradiance is reduced. So to that PV power is reduced to 210 watt. Okay. And the load we are getting, that is 388 watt in the first go. Okay. So we have first done for the constant load condition. Okay. So load is kept constant, but irradiance is varied. So it is decreased first, then again increased to the same value, and in all the cases similar situation we have tried to emulate, but at a lower power level. So VDC is regulated. Okay. Then this is the case, all the currents, the power, if you see the nature of power curves or the waveforms and the current waveforms are same, because VDC we are regulating here. This is the corresponding battery current and the supercapacitor current and the load current. And here also we are having the PV current. Okay, the supply. So, and the SOC of the battery, which is within, means it is nearly 80%. So, we have not done any power management, means we are at the low level of control. We are testing the system, so that it is, we can say ki, okay, it is doing the VDC regulation well. And correspondingly also we are having the battery, means the charging and discharging of battery is happening in a regulated manner, and the supercapacitor is handling the transient part of it. So that is our first goal, which we achieved in the first state. Then this is the again, this is first we have seen with the irradiance variation. This is the case, irradiance is kept constant at 388 watt. Okay. And we are varying the load. This is, load is varied from 200 watt to again it is increased. Okay. And if you will see, correspondingly if there is a increase in load, the bus voltage similar type of, means nature, if you will see, is a simulation and is almost the nature of the waveforms are matching. Only values are different because we are operating at a little lesser power. Okay. The DC link voltage is tracked well, and correspondingly this is the transient part handled by the supercapacitor. So battery current are like this, and correspondingly this is the SOC of the battery, charging, again discharging, again charging, like this. So after this, so two cases we have seen. Okay. So same thing we will be getting, because no Son condition we can also, because only that is similar to the hybrid energy storage system supplying a load. That will show you in a physical condition, means directly tomorrow in the tutorial class. Then we have tried the same thing with the, yesterday I have explained about you this wind energy conversion system, how we have developed the, and here we have used the same buck converter. Here now both we have replaced, that means you can see PV is replaced by the wind system. But hybrid energy storage system, what we have developed, what we have designed, same system is used here. Okay. And here we have tried to directly integrate it, because we have already developed the wind energy system. Now we are trying to integrate with the hybrid energy storage system. But what extra we are trying to do here, the power management strategy, which we have not done in the previous case, we have tried to implement with the wind energy conversion system. Okay. So how, compared to the yesterday's discussion, what I have explained, that is the wind with a single storage, and then how we are going for three case studies, that is the normal operating condition, battery protection mode, and the generator protection mode. Here same generator protection. So in battery protection we are going for the, are we operating it at MPP mode? In the battery protection, when it is overcharged, means crossing 90% or less than 50%, what I have shown, it is operating in the off MPPT or reduced power mode. So same thing we will see here, but additionally what extra constraint we are getting here, along with the SOC of the battery, we are also getting the SOC of the supercapacitor. And when one constant is getting added up, how the power management is, means the complexity in the power management is increasing, that we will see. Okay. So here the buck converter, same thing already. So just I have put the buck converter here, and directly we have tried to integrate the means wind energy system with the hybrid energy storage system. Here comes the our main thing, that is the power management. Okay, when I am talking about the power management, so it is the net power which is the combination of the power of the supercapacitor and battery power is equal to the wind power minus the load power minus the system loss or the converter losses. Okay, so this is, so here we have designed our this PMS, power management scheme, or this flowchart is we have planned such that it is operating in 3 operating conditions. That is, one is power sharing mode, that is the operating when the battery and supercapacitor SOC are within our safe operating limit, means it is within. So here I have reduced the operating means lower condition to 40%, so 40 to 90%. Okay, so here if you will see in terms of power I have given, so same thing can be, if you will divide with, because the bus voltage is kept constant, so by V it will give you the corresponding battery reference current and the how to generate the reference current to operate, so that you can control the 2 bidirectional converters. Okay, so converter means controller we have seen, means low level of control we are doing that, we are segregating the high frequency and low frequency, means by using the filtration based technique. Okay, that is done in the lower level, but in the upper level of control we are going for this SOC monitoring, and then we are seeing the sharing of the power, it is proper or not. So for that you need it is first you can check the in terms of power also, here it is checked in the terms of current, because voltage is constant. So whether the net current is greater than 0 or not. Okay, if yes, okay, net current is 0 means you are getting excess power, it is the excess generation, means generation is more, so we can go for a charging operation, and then you will check, after checking okay it is a charging operation, you will check the supercapacitor battery means SOC of the SC is whether it is less than maximum or not. Okay, if it is less than maximum, okay, SOC max means it is less than 90%, then you will check whether battery is less than maximum or not. Okay, if yes, then it is less, means it is safe. Okay, so we are going for power sharing mode. Okay, and when it is the reverse, means SOC SC is greater than SOC SC max, means it is already the supercapacitor is overcharged. Okay, so what you will do, you have to go for, you have to operate the battery, that is the battery alone mode operation. Okay, means you will discharge the supercapacitor because it is already overcharged, and you will operate the battery. Okay, so and extreme mode is the case, third case, when both battery and supercapacitor are either overcharged or in the deep discharge condition. Okay, so for these 3 cases we have tried to analyze, means formulate the power management scheme and try to implement it in the this logic is implemented in the our power management scheme, so that it will switch the mode. Okay, it will switch from either MPP mode to, means for the because here again one generation, so wind power either operate will MPP mode or off MPPT mode, and again the third case we have not considered here, that also you can add going for the generator protection mode. Okay, so because adding one condition again so many complexities are happening. Okay, and the your mode selector, the power management schemes should be sufficient, means intelligent enough to decide to switch from which mode to what mode, means depending on the seeing the condition, so it has to be done it online, so it has to be fast also. Okay, so this is what exactly I want to say, ki when you are adding a system, then how many constants are increasing. So it is increasing the control complexity, implementation complexity. Okay, but it gives it improves the system overall performance, efficiency, it gives a better result. We can tell, okay, our whatever design system is a very well designed system, so it can switch seamlessly from one state to other, okay, very smartly, or seamlessly it can switch. Okay. So this is the normal operating mode, so I am not going to elaborate more on it. So either it is discharging or charging depending on source, whether excess power. If wind power is more, then it will charge the battery and charge the supercapacitor. Supercapacitor will, means normally it is battery, and supercapacitor will come into picture when there is a change. If there is with wind power more, again we are changing the wind velocity. So again there will be excess power. So battery will take the steady state part, but the transient part will be taken by the supercapacitor. Okay, so that is the normal operating condition or power sharing mode we are saying here. Then in the battery means alone mode, here is the clue. Means if you will see, this net current is more. Okay, SOC battery is less than high. Okay, so battery can is safe, but supercapacitor is overcharged. Okay, so here what we can do, so supercapacitor will discharge, and if it is the reverse, if means battery is more than the lower operating limit, means battery is in the safe condition, but supercapacitor is less than the load threshold, means less than 40%. Then in this case, when it is less than threshold, you will charge the supercapacitor, and when it is more than the the supercapacitor is overcharged, you can say, then it will discharge. So how it will discharge? So that is why I am saying it is battery alone mode. Battery will operate, but supercapacitor is not now taking place for the transient operation. It is either in this case it is discharging at a constant current. Okay, with the result it will be more clear to you. And in this case, when it is less than the load threshold, so it will charge with a constant current charging. So it is now not taking, means the transient part is not shared by the supercapacitor only, so that's why it is called battery. Battery is again because to safeguard the supercapacitor here. Okay, is it clear? So, and this is the extreme mode when both are either overcharged or deep discharge condition. So in that case we cannot take any risk, we have to go for the battery protection mode. So both the reference current are set to 0, means both the bidirectional converters are in the floating mode. Okay, we are generating a reference current, 0 reference current, so it is tracking that. So now who is only present there, but we need a bus voltage regulation. We cannot, because if we are not going to regulate bus voltage only with the wind, so it will again either give a more voltage or there will be a drop in voltage if wind power is less. So what is the solution? That already yesterday's class I have discussed in detail. That is we are going for the wind will switch to reduced power mode. Okay, so this is the, so battery, both the components will stop. Okay, in both the cases, whether it is greater than 90 condition or less than 40 condition. Okay, so that I will show you in the during the result. The battery will the wind will switch from MPP mode to off MPP mode. Here it is reduced power mode. Okay, and as the bus voltage will be regulated by now. The converter is the buck converter, which is operated, which will be operated in the closed loop mode. And if wind power is less, load demand is more, then we have to go for a load shedding condition. Means you have to reduce the load also. Okay, so this is the complexity. One only you have added only one component. Okay, but in the here in the operating condition, so many conditions are arising. Okay. So for all these three conditions, now we will see the implementation part, how this is the same scenario where we have just added, this is the wind setup that I have shown, okay, where the supercapacitor pack is added, and so battery is also reduced here, means instead of 36 volt we are going for a 24 volt battery system. Okay. So similar setup, this is a buck converter for the wind setup, okay, and this is the two bidirectional converters I have shown separately. For the while developing for the PV and wind a little different way we have developed. Okay. So other things are almost same, and it is the overall single line diagram. Here we have tried to show this how it is integrated with the through the DSpace digital controller. That will be explained in this is the battery means hybrid storage, this is the wind with the same system. Okay. So this after developing the test bench and testing individual components, we have gone for the its implementation. Okay. Here again the for if you see the results I am showing directly, that is a what is the in the power sharing mode, what you can see the battery and supercapacitor are here. Nowhere we have first because of the storing the result so many things, so we have not taken the supercapacitor SOC here, we are only showing in terms of battery SOC, and the supercapacitor you can see the corresponding power level, it is reflected the current, the corresponding currents are shown. Okay. So here clearly when there is a this is the load power is it is operating because it is a wind system, and whatever machine we have chosen, this is operating means available output power is means efficiency is less. So we are operating maximum up to 200, less than means 190 watt we have gone. So here the at 6.5 meter per second we are getting a wind power of 150 watt, and the load power initially we have operated at 105. Okay, if you will see this 0 to this time 25.74 second, the load and the wind power is constant. So then at this point 25.74 second the load is changed to 190 watt. Okay. So load is changed to 190 watt. Here if you see the battery is taking 30 watt previously. Now when further there is an increase in wind speed condition, the load is increased, the now previously battery was taking, now it is discharging because the generation is 150 watt and we have load to supply 190 watt. So rest power is, and the system loss for all three converters we have now, 2 bidirectional converter, 1 buck converter, so it is almost nearly 55 watt. If further also it can be reduced, but in our normal system we are getting this loss component overall. Individually we are not measuring, whatever difference is coming, so that we are considering as a loss occurring in the converters. Okay. So first case is the load change condition, then there is a wind speed change condition here. Okay. When there is an increase in wind power from 150 watt to 175 watt, okay, load remaining same. So here load increase, load decrease, then wind power increase. Okay. So in all these conditions, so whatever you have seen during wind speed change, is there any effect on the load power? No. In the similar type of characteristics you have seen in case of the PV also. So when that means when we are operating our renewable energy sources in the MPP mode, the load change is not going to affect it. Okay. So that is what I want to conclude from this. You should be very clear on that. If you are not getting it, is your load is also fluctuating with your MPP, that means your MPP is not tuned properly. Okay. So you have to again design or manage the algorithm properly. Okay. So these are the, you just see supercapacitor power or supercapacitor current when it is coming into picture, when there is a transient, whether it is a load transient or it is a wind speed change, because it is a single wind with hybrid energy storage. And for all the cases if you see this is a wind, here you will, in case of PV you are getting so smooth, but here oscillations are more because you are getting operating the wind means the generator. Okay. So here the DC bus voltage is regulated, means the actual voltage is tracking the reference voltage here, and correspondingly here the battery reference current is also tracked by the actual current. And supercapacitor is also doing the same. Okay. And this is the corresponding SOC of the battery. Okay. So this is the case when it is a, either you can say it is a power sharing mode or normal operating condition. Okay. But what is the change when we are coming for this battery alone mode? Battery alone mode, what I told, it is the supercapacitor, two cases, when it is more than 90% overcharge condition and less than 40%, that is the deep discharge condition. Overcharged condition, it need to be discharged. So how it will discharge? It will discharge, you have to give the, now reference current is not coming from the this filtration based technique. Now you are giving a reference, generating a reference current at a constant current rate. So the supercapacitor, if you will see, ISC is discharging at 2 ampere rate. Okay, we have set, means that is, it is not necessary, depending on the maximum rating you can decide. We have set the reference current to 2 ampere. So supercapacitor current is positive, you see, it is discharging. Okay, and battery is, now you cannot, means it is the load power is constant, the PV power, the wind power is constant. Okay, and the battery is taking how much? 105 watt, load is 105 watt, battery is charging at 98 watt, means it is taking, storing, and correspondingly the this is the battery current. Okay. The difference you try to understand here, when you are trying to safeguard the supercapacitor, so only battery is operating again, hence supercapacitor is only discharging because it is in the overcharged condition, and this condition also the battery, the DC bus voltage is maintained constant, and already you can see battery is charging here with a negative, means less than 3 point something current, and this is also visible with the SOC. Okay. Then same thing you can see for the battery alone mode when it is SOC is less than 40%. Okay. So battery is supercapacitor is in deep discharge condition, so we have to bring it back to its normal operating condition, so it has to charge. So we are giving a negative reference current to it. So supercapacitor is charging and following the actual current, is supercapacitor current is following the reference current. This is a reference command we are giving. Okay. So controller is changing, switching from one state to the power sharing mode to the battery alone mode. Okay. And correspondingly you are you can see the battery, the supercapacitor is charging with 40 watt, taking 40 watt, the battery is discharging because here load is more. Okay. Load power is around 195 watt, but the wind power generation is 150 watt. So battery is supplying the rest amount of power. Battery is supplying the supercapacitor is taking, and also load is getting supplied. Okay, and rest also it is loss is there. Okay. So this is the second condition. Coming to the third condition, when it is extreme mode of operation. Extreme mode, I have missed one. Okay, this I have not shown, just to it is similar, only less than means overcharge condition I have not shown here, it is in the second slide. Let me check. Okay. So it is only, I have shown it is similar for 90% case also. You can refer, these papers are already published. Okay. So you can see for here I have shown for the when it is reaching the lower limit. So there is a, this is the nominal load of 195 watt. Wind power is when it is changing, means it is operating in the MPP mode. When it is reaching or touching the battery SOC, and the SOC of SC is reaching the 40%. So it is switching from MPP mode to the reduced load mode or the reduced power mode. Okay. So, if you will see, because here two things are done separately, because this load changed till now we have not done automatical. So, manually we are changing. So, it is taking little more time if you will see. Load shedding and switching from MPP mode to the reduced power mode or off MPP mode are done together. But again this 48 volt is tracked, means the actual DC link voltage is tracking to its reference value. Are you getting? And what else here you can see, to protect the battery and supercapacitor, both it is tracking the zero reference current. You can see here, this is the extreme mode of operation. Same thing is possible, you will get in the reverse way when it is crossing 90%. So, that is why it is a repetition. So, I have not shown. Okay. So, in this way for all three modes our power management scheme is working well. Okay. So, we have seen single PV with HESS, wind with HESS. Now comes the last part of it, that is PV, wind with HESS. So, this is the architecture. In now we have changed the converter, means both are buck. Okay. Yesterday this PV, wind, I have shown these three things. This this was supercapacitor was not there. Okay. PV, wind and battery, but now we have introduced the hybrid energy storage also, and because to match the, means as we are using a PV emulator, we have to match the voltage level, we have replaced yesterday's system. I have shown it a boost converter if you recall, so with the Arduino implementation, but now all things are integrated to this dispatch controller, having these two are buck converters. Okay. And we have tried to implement it. So, this is the power management. So, here one more source is coming into picture. So, somewhere I have mentioned RES, means renewable energy sources, two sources. So, the net power is equal to, now one more source is getting added up, and rest thing is, so net power is the battery plus supercapacitor. Okay. So, and accordingly the reference current is getting generated. So, I am not going to again repeat the same thing, because just now you have the idea when we are going for the MPP to off MPPT mode, when we are switching to the battery alone mode, means when, because with adding this supercapacitor and adding one more source. But when both the things are off, if for this system two sources are there, we cannot allow it like that. Okay. So, to start it also there has to be, either you start the wind system, then regulate the bus voltage, then integrate, insert the PV, or you start the PV, regulate the bus voltage, adding the hybrid storage, then insert the wind. Either way you can do, but when both of them are off in the protection mode, you cannot allow these two to operate. Till now we have not developed for that system. It can be also done for, if you will improve your power management scheme, means adding some more better controller to it. Okay. So, that is another part of research. So, till now we have not achieved that. So, this is here we are either turning off one of the source and we are regulating that, with the other source we are maintaining the bus voltage, means power is, means the load is getting supplied through either of the source, means either you will switch off the PV or you have to switch off the wind energy system. Okay. So, this is the thing. So, here now you see the how the power management, this again flow chart is increasing, conditions are increasing, and if you will check, and you may ask me, madam, you have not considered that condition, that may also occur, because we are human being, there error can occur. So, what I want to show, again this excess generation mode, in different way we have tried to again develop our power management scheme. One source we have added a storage, one more storage added, again complexity increases. When we have two more sources, means two sources together, if you are going to add, which we have started working on that, if you are going to add the fuel cell to it, you think what will be the complexity. Okay. So, again we have to put the, okay, we have achieved in simulation we have done, but hardware implementation till now we have not done. One of our student is working on this. This work what I am presenting now, it is recently done by my PhD student. He got awarded, Pradimna Kumar Behar, and we have many publications from this work actually. Okay, so this all the work recently, means this month only he got awarded with this. This is a whole thesis work. Okay, so you think about the time, more than around 5 to 6 years it took to achieve all this. Okay, so for this also we have implemented successfully. This is the wind battery and PV. We have replaced the PV that lamp system with this PV emulator. So all the 4 are here: 2 source, 2 storage. Okay, and again different modes of operation. Same thing, this power sharing, this supercapacitor discharging, supercapacitor charging, and off MPPT mode is the extreme mode of operation. Okay, so this from these 2 works we have around 2 or 3 transactions. Okay, so here I have referred, you can go through the detailed results of it, but similar kind of results, so I am not repeating it. Okay. So you just see test conditions. Here what are the conditions? Wind speed variation. With wind speed variation, how the results are coming, keeping the load constant. Load variation, then you can vary the irradiance variation. Okay, no sun condition, no wind condition, many things will come into picture. So some case studies we have done. This you just see, wind WPGS is shut down. We are operating at this wind power is 0. So all the system is, whole system is tested for all operating conditions. Okay. So these are the results where this power management scheme, along with the power management scheme, MPP and battery charging discharging, supercapacitor charging discharging is happening. So here all these things are shown, means with the irradiance variation, this is load, all test conditions are shown, means in the normal operating, because the battery and supercapacitor is within the range. Okay, and later we tried to take the supercapacitor SOC also, but here I have not shown. Okay, so that is also if you want. So first is here the wind, the solar was solar with, but hybrid energy storage system was operating and wind is introduced. Okay, then you are changing it to this load power is changed. Okay, so for all this wind power change, irradiance change, we have seen that in normal operating condition it is capable of tracking the DC bus voltage or maintaining the DC bus voltage, and the charging discharging also happening properly. This is supercapacitor. If you will see here, supercapacitor, you just see here one condition when supercapacitor is overcharged. Okay, so it is supercapacitor overcharge means it should discharge at constant current. So that is also seen here, if you will see. And again, once it is coming to supercapacitor is discharged and coming to the original level, then it will take part in again the taking the transient cases. Okay, which is happening here. So all modes are, means for all operating modes, again on that all means when there is a mode change, there the system is operating well. Okay. So this is the case when the supercapacitor is reaching the load threshold, means supercapacitor is charging, then it is again taking means actively participating in the taking the transient part, that is shown here. And for this case, DC bus voltage is maintained constant. Okay. And when this is the extreme mode, when both are here, again SC is missed, I have not shown because of the space constraint. Okay, battery is reaching the lower limit, this of MPPT and load shedding are happening. Okay, so this performance can also further be improved. We are trying for it. So there are means what I want to conclude from this, that So this power management scheme we have analyzed in one way. So you can think of some other conditions, you can use it, you can make it more faster, it can be made more efficient. Okay. So there are lot more to work on this area. Okay. So as already this is the fuel cell, I have already given one clue where you can start also if anyone is interested. So from this we can conclude that this what we have developed, this low voltage DC microgrid, I am saying it, PV, wind, energy based, PV, wind and HESS based self-sustaining autonomous microgrid, or this means it is operating in a standalone mode. Okay, any name you can give, autonomous, standalone, off grid mode. Okay, that doesn't matter, and for all operating conditions it is operating seamlessly. So this system, for is the application area why we are trying to we are so much interested to develop this. So this is because this 48 volt system is upcoming bus voltage level for a DC based system for this rural home applications, okay, or domestic applications. So that's why, and also for EV charging, that also we have started working. Okay, and apart from this, we have also this, if you see the wind system, we have taken, I have shown everything here with the squirrel cage induction machine. So we have also parallelly worked, and one more student is already got his degree from a PMSG based system. PMSG, but instead of a buck converter, because there we have done with a bus voltage of 220 volt. Okay, that is for another application. Okay, so for that, so buck converter is replaced by, for wind system we have replaced it by a boost converter. PMSG machine is changed to SCAG to PMSG, and that also we have implemented. So this type of work means you can do for different applications. You can choose your bus voltage accordingly. You can do the exercise of designing whole thing, and then doing the simulation, then going for implementation. So this is what I want to say, and mainly this lecture I focused for this to the power management. But after some time we are going to start talk about the MPPT of a single system. Okay. And in the tutorial part, one simulation also my student will show there. So these are the some of the journals we have published from this work. Okay. Only means some are I have shown, few more are also there, 10 I have shown here, and these are the references. So if you have any question, you can ask me. Any question from the audience, online participants? So we can stop here then. Thank you all. all of you? Okay, I am going to start the tutorial 1, that is design of power converters for solar PV system and the MPPT algorithms. Just previously I have been skipped as I am going to elaborate it, and one simulation will be shown by my PhD student K. Vikas Verma. After first I will just start about the basics of the power converters, its design for the PV system, okay, and then the basics of the MPPT algorithm, then how we are going to simulate it for different type of power converters we are going to explain in detail. So already as I told, this DC-DC converter design, the types of MPPT techniques I will be explaining in first part. Then the operation of SEPIC converter, the design and the simulation of SEPIC converter for this MPPT simulation for this PV system will be explained by my PhD student K. Vikas Verma. So coming to the MPPT techniques we are going to implement, before that the system what we are considering for a PV, when already as I have mentioned, this PV system we can have a two-stage, or if you are having a AC, it is connected to AC grid, and if it is a directly connected to the DC grid, we need a DC to DC converter only. So that's why our single stage connected to AC grid, we have a DC to an AC converter. So where it is trying to, the main work of this converter is to track MPPT, or it will try to track the maximum power. If you, so what is the MPPT controller? So it is not a mechanical tracking. So by using any of the MPPT algorithm, where the algorithm is going to track and give a generate a pulse, so which is going to control this converter, means the duty cycle generated by this MPPT controller is regulating this converter, so that it will give an output, so that the system will operate at MPPT or maximum point, that is the maximum power point tracking technique we are telling. So before coming to the technique, so what is behind it, means, and what are the possibilities of converter when I will cover only DC to DC converter. Already I told the options are buck converter, boost converter, buck boost converter, or SEPIC converter, chuk converter, any type of converter depending on your application area or your requirement, simplicity, whatever, what are the, when we are going for this MPPT operation, we will see for that. But coming to the characteristics, what is the, why, means if you see the this IV and PV curve which is merged here. So this is the IV curve, okay. So this is the operating the load line, we are depending on your operating means load variation or operating condition, it will shift between this to this part. But how this power converter is playing a role, means the operating point, how it is changing between this, either this is the PV curve and this is the IV curve and this is the load line. So it switches between this point to this point, means either it moves towards the left or right. So that depends on your how you are controlling your converter, okay. And these characteristics also totally depends which converter you are choosing. So accordingly this load line or the load you have to choose, so that you can will be able to track the maximum power. So here coming to, so three options, so all for three cases I will show you how the load line is changing. So when I am taking a buck converter, for which if you will see the, when I am talking about MPPT control, so what exactly it is, means we are going for a impedance matching, means the load impedance should match with the source impedance. So source impedance, so that is the internal or the reflected impedance, you can say internal impedance, or the in DC system you can say it as a simple way, it is a resistance only. So if you for this buck converter, we know this relationship, the output voltage is equal to the duty into the input voltage, and from that we are getting for a lossless system, the internal resistance is equal in terms of the load resistance is RL by, if you will do this simple calculation, if you will use these equations, you can see it is coming in terms of RL by duty ratio square, okay. So that means if you are varying this duty ratio, so you can vary this operating point accordingly. Okay, so if you will see, so if for duty ratio, if we are keeping in this ideal cases 0, that means your input impedance or the input resistance becoming what? Infinite. And if it is D is 1, it is D is 1 means our internal is equal to, or the input is equal to the load resistance. So that load line, if you will see, it is varying between this point. Okay, it is below the operating maximum point to this side, right side. Okay, and so this is the case when I am taking a buck converter, and when I am changing this buck converter to a boost converter, and in the similar way we are going for a lossless system. For the simplicity, we have taken the output power is equal to the input PV power. So in that case, if you will do the same way, try to derive, you will be getting the internal resistance, the input resistance in terms of the output resistance or the load resistance is 1 minus D whole square into RL. So by putting D is equal to 0, so what is the starting point here? And when I am choosing a boost converter, so the load line or the operating point moves between this to this side, means left side of it. So operating zone is getting limited, though okay, to meet the voltage, to match the voltage, so we are choosing our converter blindly, but accordingly also we have to see in which zone we are operating. Okay, so but second, in the third case, here I have shown because we are going to simulate this SEPIC converter, but same is the case for if we are instead of SEPIC, if we are going for a normal buck boost converter also, you are going to get this relationship. Okay, similar way you can derive, and you can find out the internal R input, R internal, this take it as same because it is same reflected resistance. So here, but what is the advantage we are getting here? We are getting both the operating zones. Means it can move depending on this 0, this D square by 1 minus D square. So if it is 0, so what it is? 0. Okay, so this full, if D is 1, then it is infinite. So it is not limited to, so it is full zone of operation we are getting. Okay, if by varying the duty, we can operate in the full region. So that's why you can go for this SEPIC converter, but if you want a simple implementation, so you can, depending on, in that case, depending on the bus voltage level, you can either choose buck or boost. So though it is limited to either side, but you can go for that buck or boost converter implementation. Otherwise, this SEPIC or buck boost or a choke converter, you can also implement. So this is the operation of it, the design of it will be explained shortly. But before that, I just want to tell one buck converter. I will show one example with the buck converter. Here, this whatever system I have shown just before, 1 kilowatt system, the buck converter I skipped at that point. But as we have taken the 1 kilowatt rating, means it is designed for to meet the load demand of 1 kilowatt. So from there, we have tried to design the buck converter in the normal way. So the design means here it is the, what is the maximum load, current it has to supply, means load current, then the parameters, the filter parameters, the LPV, the output and input capacitance is calculated, okay, by using the usual our design technique, means how to design parameters of the buck converter. Okay, and for this here the current ripple is taken to be 20%, and the voltage ripple is designed taken to be 1%. So this value is how much ripple you are allowing, that is totally in your hand. So you can make it tight 10%, you can make it 1.05, because may explain with a 2% voltage ripple. So this is means given the design guideline is between 1 to 2% or maximum 3% you can go for the voltage ripple, and the current ripple is between 10 to 30%. Okay, so taking that, the operating range, the duty is calculated to be 0.4 here. Okay, so this is the one simple example I have given. And how it is when you are going to simulate it, the same thing with the buck converter you can simulate, okay, to get to operate it in the MPPT mode, okay, or so. But this is the converter design I am talking about. But going for the MPPT, that means algorithm part you have to look for. And when you are going to implement or simulate the algorithm, MPPT algorithm, what are the different algorithms and how you are going to choose the algorithm and what are the constant or what are the points there you have to see, that we will see now. So MPPT tracking control, if you will give a search, you will get thousands of or lakhs of paper on it, okay. And that too PV based MPPT, though comparatively little lesser will get, but still it is more. Basically how we will broadly divide it, it can be divided into 3, and in papers also there are, depending on their requirement, they are giving the classification. Here we have taken from one paper. So this is the classical method, intelligent based method, and optimization based techniques you can tell. And in the classical we have not, till now we have not gone for any intelligent or optimization based technique, okay. So it has advantages, okay, it gives better response, but it has simultaneously the computational complexity, it takes more time, means computational burden is more. So we have just focused on this simple classical methods, and there also we are done on the P&O method for the PV system and wind system. Then we have improved it by doing a drift-free MPPT technique by improving it further, okay. And there we can have a variable step operation, the fixed step operation, that means the step size of the MPPT techniques can be adaptive, it can be fixed step operation. So all these things we have tried one by one. And we have for PV system also we have tried for this INC technique, in incremental conductance method, okay. This hill climbing and P&O, here it is given a different way, but it is the concept shows it is almost similar, okay. So because you are perturbing and observing, or you are climbing a hill, it is similar in nature. Then, so this is about the different MPPT techniques available. So how to select the MPPT, means when we are going to do the simulation or implementation. So first it is the ease of implementation, and then number of sensor also it is playing a role, giving, means how it is affecting the MPPT performance, okay. The algorithm efficiency, it is not the system efficiency, it is the algorithm, means input power to the algorithm and output. So based on that it should be more than 95-96%, we can check it, okay. So that is also should play a role while selecting the MPPT. And then also cost of implementation, it should be simple to use and implement and also less costly. But if it is like for this optimization technique and the other methods which are difficult to implement, then we are obviously to make our life simple, we are going for our normal, which is a very popular method, that is the perturb and observe MPPT technique. And we are going to implement means already we have implemented for this buck converter, that I will directly show the results, and Vikas will explain you about the SEPIC converter step by step, how to do the simulation, how to get the result, how to go for the how to tune it, those things in detail. So this is the basic P&O method flow diagram. Here how you are moving from either means searching for the MPP point, whether you are in the left half of the MPP part curve, or you are in the right half of the part, depending on what you will see. You will see the change in voltage with respect to change in power with respect to change in voltage, okay, and the sign whether you are at the left side of the MPP or right side of the MPP, and then you have to perturb further so that you can reach the MPP point. Okay, so these are the very standard stuffs. But to modify it further, we have done one, but here what is the problem with this? This tracking method suffers from drift. Means if there is a sudden increase in irradiance, okay, so this algorithm fails to detect it, okay. and increase in irradiance in case of wind, PV system, and increase in wind speed in case of wind system. For both the cases we have tested. Okay, so it is giving similar type of it. There is a mislead. So to avoid this drift problem, we have modified it by introducing one drift-free P&O technique. So that is, we are also saying it as a modified or DF P&O technique. Okay, so here for both wind and PV system, what I have explained before, we have implemented this drift-free P&O MPPT technique. So here you have added one extra term, so that is whether the change in current. Okay, so that is giving, so in case of drift, so means any change in the increase in irradiance or increase in wind speed condition, this is positive. Okay, so this by adding this search means the current information to the loop, it gives a better performance. Okay, so that's why we have modified, and here also initially for the wind based system we have referred this paper. This is also published by our department only in 2015. Now we have done modification and applied the same thing to the wind based system and got better performance. So that there also we have published a transaction in power electronics. Okay. So these are the things with slight modification also and improving the performance further. So you can have improve the overall system efficiency and performance. Okay. So this is the result of the MPPT technique having which is applied to the buck converter based system with the that PV system I have shown. Okay, this 1 kilowatt PV system with irradiance change, and this is the during irradiance change condition how the MPPT is means tracking. And here one thing previously I have not shown, there in the power performance where we are going for the power management system. So there this MPPT how the duty cycle those things change I have not shown. So you can see clearly this 3-step operation is clearly visible for this P&O technique. Okay, so when you are this perturb and observe, so this gives a, so but in case of the only P&O means where we are not going for the drift free, it gives the oscillation, more power oscillation around MPP. So that also we have avoided, we have improved it, having less power oscillation when we are going for a drift free MPPT technique. So which is compared here. Okay, so this it is giving a better result with respect to the conventional P&O. We have implemented simulated the drift free P&O, and it is giving a better performance, and also algorithm efficiency is also improving, which is given in the corresponding paper. This part is also we have published. Okay, so now the session will be taken by my student Vikas Verma. Okay, so he will be explaining the system with the SEPIC converter, and in detail. I have just give you the overall overview of the power converter design, the different type of techniques, but how exactly we are going to simulate it, he will be step by step he will explain. Okay, so it is over to you. Yes.
Thank you, ma'am. Good afternoon, everyone. Today I am going to explain the simulation of the P&O MPPT controller using SEPIC converter for PV system. So, okay, as we know that the buck converter, it will buck the voltage, boost, it will boost the voltage, but in buck boost we can use both stepping up and stepping down. But what is the disadvantage in that buck boost converter is that we are getting an inverted output voltage compared to the input. So to avoid that one, we are going for the SEPIC converter. SEPIC converter, what is the meaning of SEPIC is that single-ended primary inductor converter, where in the SEPIC converter we are extra adding one inductor and one coupling capacitor. So by using that coupling capacitor, you can see that this coupling capacitor, it is placed between the input and output, so it will be used as a isolation between the input and output, which will protect when the load is shorted, it will not affect that to the input because of this coupling capacitor. And also in buck boost converter, the switch is at the input side, so there is some discontinuity in the input current, but here there is no any discontinuity because of the inductor. It is the input is always connected to the load. So what are the main significance of this CP converter is that due to this input inductor, the harmonic low harmonic input current will be there with the low harmonic. So because of that, it will be feasible to use for the applications like battery applications or the renewable applications to track the MPPT. And also when we are using this CP converter in a discontinuous conduction mode, we can use it as a power factor correction rectifier. And also one main advantage also that in PV system we need two diodes. One is a blocking diode and another one is a bypass diode. So this bypass diode will be useful to bypass the current which has low irradiations. But the blocking diode is useful to reduce the effect of the reverse current. So here when we see the CP converter, that there is a one diode, so this diode will be helpful to block the reverse current which is going towards the input supply. So there are a lot of advantages by using the CP converter, and you can based on like if you see most of the applications will see the boost converter for the PV applications, but in boost converter the output voltage is always high with respect to input voltage. But here we can based on our requirement, the CP converter will be used, the output voltage will be controlled. It's a flexible, we can have a flexible control of the output voltage by using the CP converter. So coming to the operation of the CP converter, like when the switch is on, we can see that the input inductor will be charged with this input voltage, and this coupling capacitor it will discharge through this. This will charge this inductor, the second inductor, and also this output will be supplied, as there is no connection between input and output, but this output will be supplied by the output capacitor. But when we are going to switch off, when the switch off mode, we can see that the both input inductor and the L1 and L2, the both are supplying to the load, and also this input inductor will charge this coupling capacitor, and both inductors will charge the output capacitor to the load. So this is the operation. We can see that the coupling capacitor will be charged till V input. Because of that, when the voltage across the inductors will be the same. So because of that, we can design the inductor as both inductors in an equal way. So you can see that today we are going to design a CP converter for 2 kilowatt with a switching frequency of 20 kilohertz and input voltage of 100 to 112 volts and output voltage 96 volts. And we are taking a ripple inductor current, and the voltage will be 20% and 2%. And the load resistance based on our formula like V square by R, we are getting 4.6 ohms. So before going to, we have a output requirement 2 kilowatt, but how we will design the PV array based on that. So we have a model these parameters are taken in our college. There is a rooftop is there. So that ratings I consider here. So we can see that we have a 205 watt peak module. So but I need a 2 kilowatt. So how could I arrange modules into array? How many I have to connect in series, how many I have to connect in parallel, and how I make it, how I can meet my required load parameters. So here we are using that to, here our rated voltage is VMPP is 28.4, but I need 96 volts output. So how I can meet? So the output, the number of panels required in series, we can, the rated voltage required is 96 by the rated voltage of each module 28.04, it will give 3.42. If it is 3.42, we can consider it as a 4 module. So we are connecting 4 modules as a series to get our required PV array voltage, required voltage. So but what about the current for 96 volts? Okay, 2 kilowatt. So how much current we need? We need a 20.833 8 amps we need. So for that, but here our ISC is 7.9, maximum current is 7.91 amps. So how we can connect these strings, this series? We call it as string, means the panels, modules which are connected in series, that will be called as a string. How many strings that we have to connect in parallel to get the required current? So we can see that number of PV strings is the rated current by ISC of the module. That is, our rated current based on our 2 kilowatt is that 20.833 by 7.91. It will give 2.633, that nothing but 3. We consider as 3. So we have to connect 3 strings in parallel to get the desired current. So you can see that short circuit current is 3 into 7.91, 23.73 amps. So by this we can meet by using 4 modules in series, and strings connected in parallel is 3. So by using this configuration, by developing this array, we can meet our rated output power. So how much power it is generating? So it is not exactly giving 2 kilowatt, but based on our modules connection, it is giving around 2.47 kilowatt. Because of that, we can see that 2.5 into 4 into 3. So we can get 2.4 kilowatt. This is the maximum peak power that we are getting from our array. So with this design, PV design, we are going to calculate our what are the duty, how much duty ratio should be operate, what are the filter designs that we have to consider. So here we can see for this was done for the continuous conduction mode. We can see that we have to find at what range, because PV is not a constant power source. It is depending on the nature. So based on the insolation levels, the operation of the PV, the peak power will be changed. So based on how much we can consider, like I considered the voltage window from low voltage to high voltage. That voltage I take it as a 75%. So that 75% of my rated voltage of my array will be 84.45. So this is the minimum voltage that I am considering from the PV module. So by using these things, I have to find what are the duty ratios that I have to will be available, like what is the minimum duty ratio, what is the maximum duty ratio that I will be considered to get my desired output power. So here we can see that the same as the buck boost converter, like we can see that D is V0 by Vin plus V0. Nothing but when we consider it as in terms of V0 is equal to Vin into D by 1 minus D. So we can see what is the minimum D will be available at when there is a maximum voltage. So our maximum voltage is that 142.2 volts. The maximum voltage of the array is the 142.2 volts. So with when is there maximum voltage, our duty will be minimum, and when is there minimum voltage, our duty will be maximum. So here the D minimum will be 0.4040 and the D max will be 0.5332. So where we will use this D minimum, D max, why we are using it? This will be useful when we are designing our filter parameters. So coming to our inductor selection. So we are taking L1, L2 is equal, because I told you like the voltage across throughout the switching cycle, the voltage across the inductor will be the same, because you can see that when switch is on, this voltage will be V in, and when the inductor is this coupling capacitor will be charged to V in when switch is off. So that only it will be this voltage will be appeared across this L2. So the both voltages across the L1 and L2 will be same. So that's why we are taking as L1 is equal to L2. So why we are taking V in minimum? Because at a minimum voltage level, the peak current will be is more compared to V in max. So that's why we are considering a V in minimum voltage. At V in minimum, our duty cycle will be max. So that's why V in minimum into D max by delta IL into FSW. So our delta IL, we consider it as a 20% of our, the IL is a input current. So we know that our input current is 23.73. So based on that, the delta IL is 20% of the 23.73, it is 4.746 amps. So by using this thing, we are getting our inductors L1, L2 as a 0.474 millihenry. But in a SEPIC converter, there is one more advantage, is that we can reduce the size of the inductor. Here we are using separate inductors, but if you use a coupling inductors, then our inductor value will be L1 L2 by 2, means 0.474 by 2 it will be because of that coupling inductor. So like that is also one of the advantage of the SEPIC converter. If you use a coupling inductors, our size of the inductor converter will be reduced. So the inductor will be reduced. So what about the coupling capacitor? This coupling capacitor we can using that I naught into D max. So why we use D max means like at the D max the maximum output power will be applied, because output more output voltage will be there. So based on that we have to design our parameters based on our require like high voltage like so D max will be because the maximum voltage will be there at D max. So that's why we consider this a D max. So by using this formula we are getting our coupling capacitor value as 327 microfarads, and the output capacitor is also same, but here we are using divided by 2. So our output capacitor value is 576 microfarads. So these are the parameters which are designed for our rated 2 kilowatt and 96 volt DC bus. So these are the general steps to build the simulation model. So now I will I'll simulate. I'll show how we can simulate our SEPIC converter. How we will based on our design parameters, how we can construct a SEPIC converter, and how we can build a MPPT controller for that to get our desired output. So here, as we know that so by the steps that we are using here is that first we will create a new model in the simulation. Simulink model that we are going to design by using the blocks which are predefined in our Simulink model. So we can first we have to create a new model one by one. I can so Simulink model. So after that we created one new Simulink model. In that we have to find the blocks, which blocks we have to use. So what are the blocks we required? One is we need a PV panel, and we need the filter parameters like inductors, capacitor and resistors, and we need a switching device, active switch devices, IGBT with body diode, and one diode. So these are the blocks that we required to construct our model. So in that where we can, there is a library browser. So when we click on this library, it will be library will be open. So when we go to Simscape, so here Simscape electrical, in this specialized power system. So in this, when we click on sources, so there is a PV model, add to block. See, this is the PV array, PV module. This is a model. This one we have to make it as an array based on our requirements. So when we double click on it, so we will get the block parameters that we have to design here. So this is the parallel strings. So how many strings that we designed here? How many strings we required? So we required parallel strings, 3 parallel strings and 4 modules. So 4 series modules. So we have 3 parallel and 4 modules. So but our power is 205 watt peak. So here we have to give our array, our VOC and ISC and VMP, IMP. So our VOC is 35.55 and VMP is 7.91. 28.91 and our and VM by MB is 28.04 and 7.31. So when we click apply, 35. Okay. So when we click apply, that watt peak will be changed around 204.972. So we got the required module. What are the parameters which we required? That module will come. We will get here required. So so we are here. We are using only by changing the irradiations. What is the characteristics of our PV model that we are going to design? So we are making it array at the rate 25 degrees centigrades and specified irradiations. By clicking this, the temperature will be same, but the irradiations will be we can vary the irradiations. So after this designing of PV, we have to get the switches. So we need a IGBT module with body diode. And we need one diode. We need a diode. So we got the switches. Now we have to go for the passive plugs. RLC branch. So we need 3 capacitors and 2 inductors. So by clicking on this, we need a capacitor. So the capacitor rating will be input capacitor. We can give anything. So this is the coupling capacitor. So what is our design coupling capacitor? Our coupling capacitor is 327.9 microfarads. So microfarads, and we need an output capacitor. That one will be output is 576.9. 576. So we got the capacitors. Control R. So now we need an inductors. One is so just by changing this, we can get inductors. In only RLC branch, we can get all the parameters. So what is our L1? L1 and L2 will be 0.474. Our L1 is 0.474 millihenry. So both L1 and L2. So now we are going to connect this thing. So to sense the voltage and current, we need a voltage measurement and current measurement. So our input will be connected to the, what is the input current based on? So after that we have an input inductor. One by one. Input inductor, and it is connected to the switch, as we see here, that as you see our diagram. See, input is connected to an inductor, and then that inductor secondary is connected to the collector of the switch, and also and one of the input connection of the coupling capacitor. So coupling capacitor. Then inductor, this coupling capacitor will be connected to inductor and the diode. And this diode is connected to. So we have to connect the load. So our load resistance is 4.6. So R is 4.6. Yes. So this is our converter. So now we have to know what is the how the input from the PV, how the input voltages and how the input voltage and current and how is the power is varying. We have to check it. So for that we have to connect the sensors. Already connect the sensor and this voltage sensor. And also we have to check our output voltage and output current. So for this we have to check in the scopes. So in this you can get scopes. You can see the commonly used blocks, or you can sinks, and we see the sinks simulink. In simulink in simulink block we can go another pre-blocks, that is in sinks we can get the scope. First of all, before going to scope, we have to check the input and output current. So for that we are using a go to and from blocks, where we can make it as a proper model. So these are the go to and from. So go to, this input current will go to this go to block. So we will name it as this an IPV. Right. And another one we need one more go to. It will be VPV. So to get the power we have to multiply this IPV and VPV. So this in Simlink we can get in math operations. In math operation, we can get this product. So we got go to. This is the go to block, but from this we have to take it. So we have to use from block. From block, which one? So what are the initials you have gave for that? You have to give the same. Then only it will take from that. So it will be again, we will use go to for this to keep it as a this will be PPV. So now we got this one. We are going to measure the IPV, VPV and PPV. Now we are going to use the same go to and from blocks for this I0 and V0. So we constructed our model also, this one. So we have to calculate the output power also, how much we are getting. So for that we have to this one also we have to give it to the product. To get the P0. So we have to check what are the things. For that we have to double click on the we have three parameters. One is VPV, IPV and PPV. So for that if we double click we can go for the configurations. There we have to give 3 and the layout with 3. Right. So we can see all the 3 parameters here at a time. For that, so we have to give the from blocks, we have to connect to the scope. And like that only we have to check that I0, V0 and P0 also. Okay, now it was done. We connected PV with CPIC converter, but first we have to give the rating, like what are the insulations, what are the radiations that we are going to provide. So for that we need different installations, how it is working. To check that one, we have to go use the signal builder. We can see this. signal builder. So first we will check with 1000 watt per meter square. And with the temperature, our temperature is around 25 degrees fixed. So now we have to develop MPPT. So for that we have to write a code. So for that we need a MATLAB function block. So this is the MATLAB function block where we can write the code here. So it's already there is a predefined code. So you can see that. So this is the P and O MPPT algorithm code where we are our output required is a duty. Our input is VPV and IPV. This VPV and IPV we are getting from the sensors which we are used as a voltage measurement and current measurement. So we are using is a delta is a 0.02. It's a step size. So at what rate that it should change in steps. So based on this delta, that the oscillations will like if we give more delta, it will take more time. Like the step will be more. So if the step will be more, what will there will be a chance of missing the MPP. So we should design it in a proper way that our delta should be reasonable, that it should find the MPP point. So this is the algorithm where we see in the flow chart. Previously, as madam told that. So this is the MPPT algorithm which we developed as a code in that MATLAB function. So as we develop the code, and then we have to connect the VPV. We have to take this VPV from here as a from go to from block, and then IPV is here. For this we need to like our duty should be in between the 0 to 1. So we should keep in saturation block. Continuous saturation block. So this saturation block So our should be in between the range of 0.8 and 0.1. Our duty should be, so with from this saturation block it should go to the PWM generation. So in this this PWM generated DC, can use this one. So this one we have to give switching frequency, we are using 20 kHz. So 20 over 3, and the sampling time will fix it. So this one it will go to the switch signal. So we have to take one more from block, go to block. We denote it as S, and this go to will go to the switch. So it will become a from block. Yeah, now we develop the MPPT also. Signal generator. So we can see here so this is the developed MPPT. So So it's a signal builder which is used to give radiations based on our time. So I gave as a 30 seconds. If we can change it, like when we go for axis, change time range. If you want to 10, you can give 10 seconds or 20 seconds, whatever you want. I'll give 20 seconds. Okay. Then if you want to change the range, I gave from 0 to 6 seconds, my irradiation should be 1000. From 6 to 12, my irradiation should be 500. And from 12 to 20, my irradiation should be 800. If you want to change that one, you can change. If you want to keep this one as a, you have to click on this. And if you want to change here T and Y is there. So if you want to change it is a 600, you can change. So it went to 600. So like that also, if you want to change the time, you can change. So this one it is at 6. So if I want to change it to 5, so it will go to 5. So like that we can use the signal builder to give the signals regarding our requirement. So presently I am keeping it as 6, and this one is 500. So this is my signals that at different irradiations how my this converter and the MPPT is working. So I have to say, and one more thing is that this power guide. This power guide is important when we are using the active switches. So this power guy, here when we are using active switches, we need this one. So we have to choose whether we should be continuous or discrete. So I am using as a discrete, and I am using a sampling time of 1 micro. Okay. And I am running it a variable step or fixed step, but I am giving it as a fixed step. And this is a different kind of solvers. We can use any solver. I am using this ODU 45, and this ODU, then apply. This is a fixed step. So this fixed step size I will give micro. So now my converter is ready. So now we have to run it. So, but what is the peak power? What is the peak power of this module? So, at 1000, at 500, at 800 watt per meter square, what is my peak power? How we can check whether it is tracking on or see? If you see here, see. If you click on this PV module, here irradiations it is showing 1500, and we are giving 800. Whatever it may be, you can give any irradiations. 1500, 800 I gave. So I click on the plot. So we can see here that what is my peak power here. When I at 1000 watt per meter square, my peak power is that 2.459 kilowatt, and my voltage is 112.16. So this is it should be tracked. 2.45 should be tracked. And also at 800 watt per meter square, 1.9 kilowatt is my peak power. And at 500 watt per meter square, 1.25 is my peak power. So these are the peak powers that it should track. We have to check. So whether it is tracking or not. So we can see here, see the peak power. See around 2.45. See, these are the oscillations. Like what are the disadvantages of P and O is that there is an oscillation around the peak maximum power point. So because of that we are getting these steps. Because of that delta D, if you optimize the delta D, we can exactly get the, without this drift will be reduced by optimizing that. So for 1000 watt per meter square, my peak power should be 2.4 kilowatt. As we see here. So you can see that 2.459 kilowatt, but at 500 1.259, it should track 1.259. So it is tracking 1.259 at 500 watt per meter square. So from 0 to 6 I gave 1000, from 6 to 12 I gave 500, and from 12 to 20 I gave 800 watt per meter square insulation. So when the insulation is changing, my MPPT should track. So at 800 watt per meter square, my MPPT should track 1.98 kilowatt. So when we come, so it is tracking around 1.98 kilowatt. And also my output also. So this is my output. As it is a raised to load, so whatever power it is drawing, it will deliver to our load. So to maintain the constant power, like we should use the a battery connected to this PV. It will maintain constant voltage and a constant power regarding based on our loads. So if you want to, so I need a 2 kilowatt. I need a 2 kilowatt, but it is generating 2.5 kilowatt. So how I can get 2 kilowatt? Or you can use, you can make it as an off MPPT, and you can use a controller to make constant power. Here I am using only constant load 4.9, but all the voltage, current and power, those are varying. If you want a constant power, then you have to use any controller, and you have to use this MPPT as an off MPPT. So at each installation, so how my duty is varying. See, you can see my duty is around 0.5 when it is 1000 watt per meter square, and when it is at 500 watt per meter square, my duty is around 0.42 like that. And then when it is at 800 watt per meter square, my duty is around 0.47 like that. So based on the installation, my converter is changing its duty cycle based on the installation, and based on the output, my converter is working and it is tracking the maximum power point. So these are the blocks which I use as I show you. These are the blocks. This is the model which we developed in the simulation. So these are the results which we can see that the maximum power point tracking in each and every installation, 2.4, 1.2, 1.9 kilowatt, and the respective duty cycles based on the power level, power which is available to track that one, that the duty should also act, because it should match the that output impedance to the input impedance. So as that is the rule of this maximum power point. So to match that one, our duty should be act based on that. So this is the PV voltage when it is at maximum, and this is the PV current. So when the insulation is changing, the insulation is directly proportional to the current, maximum current. So when insulation is changing, that current will also change. So we can see that at 0 to 5000 watt per meter square, the current is more, around 24. But when it is at 500 watt per meter square, it is around 12 amps. And when it is at 800, when it is increases, again the current is increasing. So that you can see, and the voltage, you can see that it is almost same, because voltage is not directly proportional to this insulation. It is so that's why it is not changing that much, but the voltage is sensitive to the temperature. When you change the temperatures, this voltage variation will be there. So these are the results for at different radiations, whether my MPPT is tracking or not. So these are the assignment questions. So for this CEPIC and also the design of PV converters. So please so these are the references. Thank you. So if any questions, you can ask. So okay, if not, we can close this one. So don't forget to do this assignment. Okay, the next session will be started 2:30. Thank you.
Okay, so good afternoon to all of you. Welcome to this session on hierarchical control scheme in DC microgrid. So, control, as I had explained previously, first thing that is there is, let's say you have any source, you have any load. Okay, in between what you need is a power converter. Okay, but power converter is nothing but it is having passive components and active switches. But you have to control, that is the main. Without control it is nothing. Just giving pulses to the switches and converter is operating in open loop will do nothing. So what you have to do is you have to control the converter. Now when it is an inverter, we control its voltage, frequency, this we control. When it is floating, means when it is independent of anything else, that I will explain. But when it is connected to some grid where frequency, voltage, or connected to anything where the things are defined, so what we do is we control the current delivered by the converter, and that comes where it is power control mode. Okay, active power, reactive power control mode. Now when you have an inverter, or let's say any converter, forget about inverter, DC-DC converter, any converter that you have, when it is a single converter, it's pretty easy. Okay, I should pretty easy with respect to the control that we are going to discuss today. So when it is, let's say a solar panel is there, then you have a converter and you are extracting power at MPP. So that time the control of the inverter, that control of the converter is just for MPPT control that you are doing if the output voltage is defined. But when it comes to microgrid, so microgrid is not a single source, it is having multiple sources. Second thing is the grid voltage has to be maintained. Third thing is there will be connection of this microgrid with the grid also. Maybe there will be utility grid, it might be connected to the utility. Most of the cases it is connected to the utility grid. Now microgrid could be AC or DC. Okay. Now the control that I am going to explain today is mostly on AC microgrid. DC microgrid is almost similar, but with respect to AC microgrid it is further simple. Okay, so you will understand why it is so. Now when let's say it's example why hierarchical control that we need, it's like, let's say you have a bakery shop. Okay, so when you have a bakery shop, only a person or two person, one is selling, another one is making bills, will do, right? Now when let's say you have multiple bakery shops in a city, then that simple management will not do. You have some upper level. Okay, so every bakery shop will have their own shopkeepers. On top of that, you need someone who is going to supervise all of them, right? Now if you have this bakery shop in multiple cities, then it becomes further up. So this is the hierarchy that we need to maintain in order to, this is the hierarchy generally we maintain in the industry, and the same is implemented for the microgrid as well. So in microgrid what we have, in microgrid we have a grid, we have load, and then we have multiple sources which is delivering power to the grid. Now that grid will be connected to utility grid, so we'll have a control at that level also. Okay, so one by one we'll come to that. So I kept this thing very simple so that at least hierarchical control you try to understand how it is implemented and what is the significance of hierarchical control in microgrid. Now hierarchical control structure is a flexible tool to manage dynamics as well as steady state performance of microgrid, including the economical aspects. Why I am saying economical aspect? I told you that it is connected to the grid. So how much power that you have to supply to the grid, or how much power, that is the power exchange to the grid that you have to look into. That looks after the planning and then economic aspects as well. Then what are the key roles in microgrid control? If it is a DC microgrid, it is only the DC grid voltage. But when it comes to AC microgrid, it is not only the voltage, it is voltage plus frequency as well as phase when it is there is a synchronization to the grid. Okay. Now we were first DC was invented, and then there were difficulties in DC because there was a problem in transmission, so we come to AC. We come to AC, but we come with n number of complexity in AC. Again now we are moving towards DC, right? This DC microgrid is, I found there are literatures who are directly saying that DC microgrids are efficient than AC, means if you operate in DC, it is efficient than when you are operating in AC. So that's why, so even if AC microgrids exist, so we need to look after whether it is, we have to control the voltage and frequency regulation that we need to keep in mind. So voltage and frequency regulation is necessary. Some person may think that why voltage and frequency when it is grid connected? When the microgrid is grid connected, why we need to think of frequency and voltage? Because it is defined by the grid itself. But thing is, the voltage and frequency of the converter which is connected to the grid, this voltage and frequency that will give you the output power. It is the voltage and frequency and phase that controls the current, and that finally controls the power delivered to the grid. As I told you, there will be multiple distributed energy resources. So there are many resources will be available in the microgrid. So there should be a coordination, how much power who will be generating, and it should not exceed their capacity, right? So there should be a coordination so that load can be shared according to their capacity, not equally. We cannot say equally we will share the load, because according to their capacity we will share the load. So see, resynchronization will be there, that it will take care. So as I told you, there will be a control of power exchange. There is a power exchange, active reactive power exchange with the grid. Active power is necessary, reactive power is for voltage control. From voltage control, the reactive power will come. Operating cost. So we need a control, not necessarily a hierarchical control, but it is found that this is one of the best suitable control method for microgrid control. Okay, there are 3 levels that I will tell you. So this is the microgrid. So we have multiple sources. We have multiple sources which need coordination and load sharing, and this is the microgrid, and there is the energy management in between, and then we have a hierarchical control for this microgrid. And we have here we have shown the EV load as we have explained in previous lecture. Now there will be 3 layers. They say it is 4 layers, 0 layer, 1, 2 and 3. So we starting from primary layer, then we have secondary layer, then we have tertiary layer. So 3 layers that we are going to discuss. Here the innermost layer, that is the control which is doing this is as I presented that, which is the control of the microgrid. That is the primary control, that is the lowest level control, which will be doing all current control, voltage control, frequency control, everything that will be done by this primary control loop, control layer. Then we have secondary control on top of it, and then we have tertiary control. The fastest control loop will be the innermost control loop, which will take action as soon as possible. Then the upper control loop, when inner control loop settles down, then the secondary control will take action. Okay. If let's say if primary control is not settled down and secondary control, let's say you have given a work to a person, as I told you, there will be multiple shops, okay, multiple bakery shop. One shopkeeper is already doing one work. You commanded him to sell, let's say, something, and he is in that process, and immediately you told him, or her that okay, you do this one. So he or she has not finished that work, again you have commanded for another work, it cannot be done. So you have to wait for that work to be finished, then only you can give the command. The same thing that happens here, primary control has to be fast, okay. It can be slow as well, but if it is fast, then after it finishes fast, then secondary control will give second command. Is that fine? Okay, so the lowermost control, it is very simple. If you have gone through innermost current loop and outer voltage loop. Okay, so outer voltage loop generates the current reference, and current reference goes to the inner loop, and inner loop is faster, so that the gain of the inner loop is 1. That means what? Outer loop always sees that the inner loop is following the reference. Inner loop is following. So the secondary loop always sees that inner loop is working fine and I am ready to give the command. Similar for the tertiary loop, this is the slowest loop, slowest level, where it gives command to the secondary, and then secondary passes that command to the primary. Okay. So what is the role of the primary control layer? The role of the primary control layer is maintains voltage and frequency stability. So whatever frequency you want, whatever voltage you want, it is going to maintain. Okay, independent act. So these are the two contradicting things. I should not say contradicting, two different. When it is in islanded mode, there you need to define the voltage and frequency. When it is active and reactive power sharing control, then there is when it is sharing with the grid, then it is connected to the grid and your voltage and frequency is defined. You are doing the current control, and indirectly you are doing active and reactive power control. Indirectly you are doing the current control. So it is for both linear, independent of load, linear, non-linear, whatever, how load is varying, it doesn't matter, it will take care of it. Now there will be so it compensates secondary loop. So secondary loop supervise whether the command, it is the frequency and voltage command it is passing, whether it is following or not. Okay, if any deviation is there, that command will be passed to the primary loop, and it waits for the time by which it will track the. If your controllers are working fine, it will wait and it will see whether inner loop work has completed or not. Ensures electrical levels within the required values. So it will see whether references are tracking or not. So seamless connection and disconnection to the grid at this level it will look into. Okay. Now tertiary looks after this optimal operation economical aspect and manages power flow between grid and microgrid and main grid. Let's start with level 1 primary control. There are lot of tasks that it has to do. So first thing, as I already mentioned, that it has to stabilize the voltage and frequency, and let's say when this is our, if we see our utility grid, it's a immense, very huge utility grid, and you are taking power or you are injecting power is not going to affect much its frequency and voltage. When it is microgrid, if your demand and generation match is not there, there will be, there is a mismatch, generator and consumed power, definitely there will be a frequency and voltage deviation will be there when it is in islanded mode. Okay. So it has to take care of that as well. So you can disconnect the DERs, okay, properly share active reactive powers among the DERs, who is going to generate how much, and it is preferable that you should not have a communication. Without communication it is feasible. I will show you how it can be done. Without any communication, that yesterday I have shown you that for coordination we need a communication link. You can have communication link as well, but why not to have without communication link? Okay. Now whenever there is a parallel connection of anything, whether it is capacitor, whether it is a battery, whether it is power converter, there will be a circulating current will exist. It has to be there will exist. So it will mitigate. Mitigate means it will not make zero, it will minimize it, the circulating current among the power converters. Also, it will take care of the DC link capacitor, which is one of the weakest link in a system. Okay, so it generates the voltage and current references. Okay, so everything that is implemented either, so this as I was telling you, so it can be either when it is grid connected, it will be in active power mode, power control mode, and when it is islanded, it will be in voltage control mode. So PQ control mode. Okay, so this I already told you that. So in PQ control mode, active and reactive power delivered from DERs are regulated to set references. Okay, so here what we are doing, we are controlling the active and reactive power. Here it is connected to the grid, the voltage and frequencies are defined. So what we are doing, we have the inverter which is going to, so we have, this is the voltage source converter, which is, so there will be an inductor here. Generally what we do is we control the inductor current. We control the inductor current in order to control the active and reactive power. Now here what we have, you can see here, we have the source, we have the inverter, we have the AC bus, and then there is a control loop. Here they are maintaining the DC bus voltage using a PI controller, and DC bus voltage, always you remember, always controlled by active power component. DC bus voltage is always controlled by active power component. What happens when there is a need for power? So immediately the DC link capacitor tries to discharge. When it tries to discharge, there will be a dip in the voltage. When there is a dip in the voltage, the controller understands that voltage is not maintained. That means there is a sudden requirement of power, and it tries to maintain the DC link voltage. The PI controller will adjust this active component of current so that active power component, active current is controlled. This is how the DC link voltage control controls the active power flow. Now for reactive power flow, this reactive current reference, reactive power reference comes from, here it is shown that reactive power reference is given, but generally it comes from voltage control. Okay, so voltage control, we'll see how it comes. So from here we are generating the reference voltage. This also will come reference voltage, and it is reference voltage is given to the voltage source converter, which is controlling the voltage, its frequency, its phase angle, and its magnitude at this point. After this there will be an inductor, so that there will be a control of current. So in this mode, if PQ control mode, the converter, the inverter is in current control mode. You always remember this. When the voltage is defined, you always work in current control mode. So as I told you that when it is PV and then we have a converter. So if the microgrid voltage is defined, so that converter will act in a power control or current control mode. Okay. So here also, since the voltage is defined at the AC bus, it is in grid connected mode. So therefore it will be in current control. This inverter will be in current control mode, in voltage control mode. Okay, in voltage control mode, this inverter will be in voltage control mode. Okay, so this AC bus voltage is now not defined. So it will define its voltage and frequency. So the microgrid is not in grid connected mode, it is in islanded mode or isolated mode, and its voltage and frequency has to be defined by this voltage source converter. So now the voltage source converter will act to generate a fixed voltage and frequency at this AC bus. It is the responsibility of this converter. So we have inner current control and outer voltage control. So reference voltage we are giving, according to which the AC bus voltage will be defined. Is that fine? So there are two modes. One is in PQ control mode, another one is voltage control mode. Both modes are in primary level 1, primary level. This both, when it is islanded mode and when it is grid connected mode, these two modes are controlled like this. So here generally what we do is we generally use droop characteristics. Okay, droop this droop characteristics, since we have this static converters, we are using this droop characteristics. I personally feel this droop characteristics is similar to, if power system people can confirm this, there is, I heard that, or I have seen during my BTech days, there is a device called governor in power plant. There is a governor which actually, it's a ball kind of thing which rotates. When there is a lower in speed, that governor controls the steam flow, I think, and like that it controls the power flow. So same thing, power flow from different, if you have parallel connected generators, it controls like that. Roughly speaking, I think it is same concept that we have in droop control. Okay, let's see what is droop control thing. Okay, so droop control, one of the major advantage of droop control is, if it is in master, there is, I told you that droop control is not the only method that you can follow. There are master slave framework also you can follow, but that needs sophisticated communication. If you are communication, then there is a separate field that you have to implement along with the control that you have. So that communication network is necessary for coordination, which is not required for droop control method. Droop control method allows power sharing without any communication. So how it can be done, that we'll see. So each source senses local demand and shares with others by adjusting terminal voltage, frequency, phase. That is for AC droop control, and for DC droop control it's much simpler, only voltage. Okay. So like this, the information is actually indirectly communicating between the sources. So here is the droop characteristics for reactive power and active power. So active power is associated with frequency and reactive power is associated with voltage. So you can see here we have two units, everywhere we mention two units. So here you can see for DC subgrid, if you have DC and you have two sources, so then what will happen, based on how much is the voltage, you can see here for different voltage you have different power as well, but for same power you need to have different voltages. That is the droop characteristics. So for same power, either you will have different voltages, or for same voltage you will have different powers. So based on how much power that you need from that source, accordingly the voltage of that source will be adjusted. Okay, or source or whatever is connected to the grid. In case of AC subgrid, you need two things. One is frequency, another one is voltage. Both are important. Now frequency is associated with active power. So for same frequency, it will generate a different active power because their droop characteristics or droop slope is different. And here reactive power, here at different voltage levels, different reactive powers will be generated. So this characteristics will be utilized for droop control. We'll see subsequent slides. Okay. Now when it is in islanded mode, so we need to generate the reference voltage. I will come to this. Okay. So droop control reduces circulating current among parallel connected sources. So it reduces, as I told you, we cannot make it zero, but it reduces the circulating current. So coordinated power flow, proportional power sharing among sources can be achieved using droop control. I remember during my PhD days, one student was working on parallel converters. He has compared this droop control method with master slave method, and when I was discussing with him, he was praising this droop control method like anything, that it is, first thing that he said, that it's very simple in implementation and very effective. Okay. When you go to industry always prefer what is simple, because industry says that industry needs reliability. So if it is simple, if it is reliable, then it is sustained, that it will be a sustainable product. It will sustain in the market. Okay. So droop control independent, autonomous and wireless control due to elimination of any communication link. So here in conventional droop control method, what it does is, it generates it first is calculate P and Q. So if you see here, so for AC grid, AC microgrid, so you need how much active power and how much reactive power that you need. First you need to know that, Based on that, for unit 1, how much will be the voltage? For unit 2, how much will be the voltage? For unit 1, how much will be the frequency? For unit 2, how much will be the frequency? That can be defined. So, first thing that you need to know is how much is the frequency, how much is the active power and how much is the reactive power. So, reactive powers are generated then based on Drude coefficients. These are called Drude coefficient for active and reactive powers, and then it generates the then it compensates the reference voltage and reference frequency, and it generates for that particular source, it generates the reference voltage. So, here you are generating active and reactive power. Based on Drude coefficient, you are generating how much deviation that you need for voltage, reference voltage and reference frequency. Then you get the reference voltage and frequency from which you generate the reference voltage for that VSC converter. Is that clear? Okay. Now, let us see how this Drude is implemented. Okay. Now, there is so when it is connected to the grid, okay, when it is connected to the grid, so that grid voltage is defined, and then in order to control the power through this impedance, let us say this is one source, this is another source, this source you can control in your hand. This source is nothing but the utility grid whose voltage and frequency is defined. Okay, so it is fixed, it is infinite bus. Then this voltage you can control. Now you have in between one impedance you have, and then you are controlling the voltage difference across this impedance to control the current, and indirectly you are control the power flow, indirectly you are control the current. Now, if you do not have this impedance, you need to have this impedance. I will tell you why, but before that let me tell you, this impedance may not be there, okay, but definitely there will be source impedances, definitely will be there, okay, that also will come into picture, but dedicatedly we need to put an impedance here. Why? Because this source is not a pure AC source, it is a PWM output from a voltage source converter, right? It is a PWM output. So, the voltage here is something like this. So, the voltage it is generating this is the voltage. If it is a PWM inverter, it is generating this 2-level inverter, 3-level inverter, it is generating voltage like this. This is this E at an angle of delta, and this voltage is, so this point voltage is this, okay. So, this is converter voltage. Now, this voltage is defined. So, what is the voltage across this? This voltage minus this voltage. Now, if this impedance is not there, then this voltage is a what? Pure sine wave, and this voltage is a PWM wave. It is not feasible. At the same time, the voltage at this point PWM, voltage at this point pure sine wave, it is not possible. So, you need, and that is from power electronics point of view. So, you need, but from control point of view, you need an inductor here. You need an inductor at this point. Okay. Now, so you need an inductor at this point. Okay, inductor is best suited. Inductor is best suited. Why? I will tell you. Okay. Now let's find the active and reactive power equations first. Then it will be much simplified to understand. Okay. So the voltage and current conjugate. You know why this current conjugate we take, right? Otherwise, this angle will not be negative. Okay, this, if you don't take this conjugate, then it will not, current angle will not be a conjugate. A current angle, this angle will not come negative. That is why this conjugate we take. Okay, then this equation comes, and then we separate out this one, separate out this active power and reactive power equations. Now, why I told you this best suited if it is an inductor, what happens when it is a high power system, high voltage system, this definitely it is an inductor, because when high power high voltage system you need thick conductor. Okay, so thick conductors has much less resistance compared to inductance. So in that case the theta becomes, this theta becomes roughly, so if it is inductor, so this theta is 90 degree. This theta is 90 degree. Okay, that is the first thing. So if theta is 90 degree, so here we can say that this term becomes 0 and this term becomes cos theta, cos 90 minus delta, so it becomes sin theta. This is fine. Then if it is 90 degree, this becomes 1 and this becomes cos . I think this should be sine. Then it becomes cos delta minus v square divided by z. Okay, so this is simplified. Now I don't know how many of you know this. This delta value is very less. Okay, this delta value. What is delta? So let's say this voltage is this. This is the grid voltage. Okay, and this is the voltage that is converter voltage. This is the angle delta. Okay, so this voltage is Vcom and this is the E. This is E phasor. Okay, this angle is delta. This delta is nearly 0. It measures in radian. If this is nearly 0, so this becomes, so in next, so this becomes delta, sin delta becomes delta and this becomes 1. Okay, so now the Drude characteristics is, as already characteristics I have shown you, that omega is omega star minus dp p. So here this frequency is depend on, so it's a straight line equation. So this is active power into the Drude coefficient, and then so this if we take, so here if we write, so F equals to F star minus some Drude coefficient into active power P. Okay, now when this active power P is 0, then it becomes F, frequency is F. So under, this is called frequency under no load condition. Similarly, voltage under no load condition. So that is what is presented here. So here you can see, so here the omega frequency is omega star dp, the Drude coefficient of active power, into P, and this E star voltage under no load, Drude coefficient under for Q, and this is the reactive power. So this is the voltage. So these are the for AC Drude. For AC Drude, these are the two equations. So here, that is why they mention that E star and omega star are DER output voltage and angular frequency at no load. When there is no active and reactive power delivered by this, when it is not delivering, so based on that it is not delivering anything. So based on that their frequency and voltages are defined as no load, at no load. These are the Drude coefficient, and these are adjusted. Okay, so microgrid with DERs. If you have multiple DERs, distributed energy resources, then this should be satisfied. This should be, because this is what? This is omega equals to omega star minus delta omega. This term is called delta omega. How much? So actually what happens, if you know that our frequency, our grid frequency is 50 hertz. Our grid frequency is 50 hertz. But how much maximum and how much, so till how much we go from lower? What is the lower limit? What is the lower limit? No? Huh? Yes, 49.5 to 50.5. Okay, it has to be within that limit. Otherwise, there will be, if it is more, then there will stability issue may come. So here also you have to define some delta omega max, so that it should not. So if you have seen that as you are consuming more active power, the frequency is coming down, but there is some limit from no load to this. There should be a limit. We should not go beyond that. That is a design parameter and will be defined by you. So this is for each and every DERs. So this is dPn and dNn should be equals to this is delta omega star max, allowable frequency deviation. Okay, dPn is nothing but the active power droop coefficient of nth DER, and Pn is nominal power of that DER. Similarly, this is the maximum voltage deviation that we can allow for nth DER, and this is the droop coefficient. Okay, so voltage deviation. So this defines how much is the deviation that we can allow. Okay, when it is grid, that was in islanded mode. So we are defining voltage and frequency from droop characteristics. But when it is grid connected mode, so angular frequency and voltage are maintained by the grid. So only thing that we have to do is the active and reactive power references has to be generated, which can be done using these two equations. So reference is there, actual omega, and then droop coefficient. If you can divide, if you know the droop coefficient, then you can generate the active power reference and reactive power reference. Okay, now dynamic response. Okay, dynamic response. Now, if you linearize these two equations, if you linearize these two equations, this equation, so first we will come with this active power equation. If you linearize it and use this droop characteristics, then what we can have is delta P, the change in active power, is equals to G into delta. So G is nothing but around this operating point where you are linearizing it. So around that operating point, G is defined as this, and then the delta is delta is the how much is the variation in the delta, how much variation that you need in the delta. So here when G is defined, so using this equation, so here using this equation, this is the small signal model for active power controls. So what it does is, how much is the active power deviation that you, how much is active power change in active power that you need, and then how much is the reference frequency, change in frequency. Okay, so what we have here is, from here using the droop coefficient, what we can have is here we are delta, we are generating so delta P multiplied G using, so this is the equation, that we are following. So delta omega star dP into delta P, then we get delta omega, this equation, and then if we integrate it, we will get delta. Okay, so here if you see delta is the angle, phase angle, and this is the change in frequency. By integrating it 1 by S, we can get delta delta, and G is nothing but delta P is nothing but G into delta delta. So these three equations are implemented here, where delta omega star is this delta omega star we can generate from here. Delta omega star we can generate from here. So delta omega equals to delta omega star minus dp into delta p. That equation is also there, this equation, and then using that we can generate the delta p. So this is the transfer function. Here if we adjust this dp, then time constant of this closed loop can be controlled, right? So during dynamic change in active power, so this is how we can control, by controlling the delta omega. So this is the variable that you have to control, by which you can control the active power. And this is only valid. One assumption was that assumption is very crucial, and sometimes it becomes not valid as well. We have assumed that this is an inductor. That is valid for high voltage, high current application, where your impedance comprises mainly because of inductor and your resistance is low. If your resistance is high, this linearization may not be true, and that control loop may not work, and that is why this may not be very well suited for low voltage, low power microgrid, where your inductance, you cannot linearize like this. You cannot assume that theta equals to 90 degree and you can arrive this equation. Try to understand, whatever we are implementing all depends on these two equations, and then we are linearizing those two equations only. So that is only possible when our assumption is theta is 90 degree for Z is majorly it is inductive in nature. Okay. Similarly, since this is for active power, similarly for reactive power also we can define H, and we can calculate the reactive power deviation as well. Okay. So here actually one small adjustment has to be done here, because it is dependent on, actually it is trying to the voltage you are trying to correct, and voltage itself is varying. Okay. It depends on voltage, and voltage you are trying to control. So that is why an extra thing that you have to implement with an integral controller, so that it is called adjustable reactive power control. Previously that was not necessary, but also people implement for active power also, adjustable active power control also implement. There are literatures available. So here this reactive power, since it is dependent on voltage, it is implemented with that as well. Okay. Now what are the drawbacks of conventional Drup method? It is one variable dp. Okay, so it impossible to satisfy more than one control objective. Okay, so active power control that you are doing, that is sufficient enough for it. So as I told you, assuming highly inductive impedance may not be true for low voltage transmission lines. Okay, this is one of the major drawback. So that is why people don't go with conventional Drup control method. They go for other modified method and all. Okay. Reactive power control may significantly affect voltage regulation. That is, as reactive power is directly affected by voltage, which I already showed you that adjustable reactive power control that is to be done. Okay. Now unable to distinguish the load current between the load harmonic current and circulating current. So these modifications people have done, and also people have proposed many work on this, but I am explaining the conventional method in order to understand the base of that control loop. Okay. Secondary control. Now primary control I have explained, which is level 1. Now in level 2 control, so control at level 1 may cause frequency deviation in steady state. Okay, it may happen. Okay, if it is not there, fine, level 2 will be happy, but if it is not, then level 2 will try to correct it. Okay. So as I told you yesterday, this is done using storage devices. When there is a mismatch, the storage device comes into picture, and it will try to compensate whatever the active power compensation needs to be done. Okay, that is the role of storage devices. So storage device will come into picture, but definitely for longer duration it cannot do. It is for your home inverter, the inverter that you have at your home, it will run for 4 hours, 6 hours, not for 24 hours, 3 days, 4 days, like it is not possible. Then you have many batteries to be connected in series and parallel. So then it is more cost, and also you have to design the larger storage devices. Centralized controller compensates and restores voltage and frequency. This is what the level 2 control is. There will be a centralized controller will supervise and will try to compensate and rectify. So as I already explained, it has to be for stability, it has to be slower than inner loop to achieve decoupled dynamics of primary and the secondary control loops. Primary has to be settled down, then only the secondary control will come into effect. So it sets reference voltage and frequency for level 1 in grid connected based on power references, and in islanded mode based on individual voltage and frequency references. This operations, so it generates the voltage and frequency. So let's see how it can be done. So grid tied up voltage and frequency of main grid is the reference for grid connected mode. So here this is the secondary control. In secondary control, what we have, this is the to primary control. These things goes to primary control. What are these? Frequency and voltage. This frequency and voltage goes to. Now, if there is any deviation, so the frequency and voltage are set from the in secondary. This is the secondary control. This frequency and this comes from, I will show you what tertiary control is going to do. There are two modes. One is grid connected mode and another one is islanded mode. When it is islanded mode, it is predefined voltage and frequency. So that will take and it will pass to the primary control. So it is secondary control and this is the primary control. So when it is in islanded mode, these are the two references, voltage and frequency references, which will pass from here to the primary control, pass to the primary control. Now, if based on the references that is generated from tertiary control will generate voltage and frequency command, which will pass to the secondary control. Now, secondary control will see whether this voltage and frequency reference generated from primary, coming from primary, whether it is tracing whatever references it is passing from tertiary. So from tertiary it is giving some references, and in secondary it will check whether under steady state this work is done or not. It will check. If it is not, it has its own controller which will control and try to track those two references in primary control loop. Okay, primary control loop will independently work. Let's say it is independently working and setting the references for voltage and frequency, and it is trying to track. Now, secondary control, what is the role of secondary control? It will see what references are set by tertiary control, it's above control. So it is taking from there and then it is passing to the lower level, and it is checking whether this is tracking whatever is commanded, whether it is tracking or not. If it is not tracking, it has its own controller, it will compensate, and then it will pass those references. It will update the reference for the primary control. Primary control has its own reference. Now, this will take references from tertiary level, and it will compare, and then it will set references for the primary control and let the primary controller to track those references. This is the simple role of secondary control. Now, in tertiary control, what it does is, it is the last and the slowest control level. It considers the economic concerns for optimal operation. Actually, tertiary control is the main supervisory control. It looks after down the line, it will see that it's a black box. It will see only how much power it is delivered and how much power it's, means from grid point of view, it will see how much it is delivering to the grid, or there is how much is the power exchange between the grid and the black box. It will see. So it will see based on its optimal and economical concern. it will see whether this much power I should take or I should give or not. Accordingly, it will set the references and pass to the level 2. Now, level 2 will see whether the primary one is tracking this references or not. Okay. So, it manages. So, mainly this manages. It actually manages means it is the one which sets the reference power that is to be delivered exchange with the main grid. In grid tied mode, the power flow between microgrid and main grid can be managed by adjusting amplitude and frequency of DR voltages. That tertiary control doesn't understand. It only sets and passes it. Active and reactive power outputs are measured and then compared with corresponding reference value will show you to obtain frequency and voltage reference using separate controllers. Okay. So, we will see. So, here what we have. So, from grid it measures the active and reactive power, it measures, and then it compares with its reference. It will set it what reference it has its active power and reactive power references it has, and it will measure from the grid. If the grid active power, let us say active power is less in the grid, what it will do, what it should do, how finally what it will be done. Let us say active power is less, okay. So, what finally what parameter is going to be affected and what parameter has to be adjusted by the level 1 control, which parameter? The frequency parameter. Okay, the frequency reference it will, because the active power is adjusted by frequency, reactive power adjusted by voltage. It will see whether this is tracking or not. Using its own controller, it will generate references and it will pass to the level 2. So, here this is what I have shown you. This is coming from primary, this is coming from tertiary control, those references, power references. So, power reference here, the actual powers and the reference powers are compared, then their PI controller, it will generate reference frequency, reference voltage. This reference frequency, reference voltage will pass to this, from tertiary control it pass to this level 2. So, reference frequency, reference voltage, and the secondary control will see this reference. It has no information about power, it has information about frequency and voltage. So, it will see. So, from primary control it will sense what is the voltage and frequency. If primary is happy, primary is seeing that okay, I am tracing, he is happy, he does not know whether power reference is met or not. But secondary control will see whether it is meeting the required frequency and voltage or not in grid connected mode. If it is not, it will compensate. If it is, then it is fine, then require active power is generated. So, if it is met, then actually this will be 0. This 2 will be 0. Sorry, this 2 will be 0. Nothing will be there. This 2 also will be 0, because it is this actual power and reference power are tracking. So, this is how the 3 level of control is implemented for microgrid and for control of active and reactive power exchange between the grid and the microgrid. So, lower level is the fastest one, the upper one is the slower, then slowest one is the level 3 control. Okay. Level 3 control based on active power and reactive power references, based on it sets references, frequency and voltage for AC microgrid, sets reference voltage and frequency for the lower level, which is level 2. Level 2 checks whether this voltage and frequency are set by tertiary control is tracked or not. If not, it has its own controller, it will set compensation frequency and voltage for level 1, and then it updates the level 1 voltage and frequency, so that the actual voltage and frequency can be tracked. Okay. So, this will be updated, this delta omega will be updated. Okay. So, this is how 3 level of hierarchical control can be implemented for a microgrid in order to extract the required active and reactive power from the grid. Okay. So in conclusion, the robust control of microgrid in grid connected islanded modes of operation faces several challenges. Okay. As I told you, when it is single shop and you have shopkeeper, one shopkeeper, it's fine. But when you have multiple shops, when you have multiple shops in multiple cities, then it becomes difficult and you need this superior control. So I also proposed one work which one PhD student will work, where there will be microgrids with hierarchical control and they will communicate with each other. So when microgrids communicate with each other, then it is the upper level, the tertiary level where they communicate. So there is a communication link needed in between, so that they can communicate about their active and reactive power demand at individual level. Okay, so accordingly they can fetch and they can deliver to the grid. So tertiary level control will communicate between the different microgrids. Hierarchical control structure suits best to mitigate most of these challenges. Levels are primary, secondary and tertiary control layers. Primary control with conventional loop control is explained, and challenges associated with loop control method is decoupling of active and reactive power control loop. This is a challenge. Also the challenge is when that challenge comes into picture when your assumption which is theta nearly 90 degrees is not true, then this challenge becomes more prominent. Okay. Level 2 and level 3 are the slower and slowest control loop respectively. So all are important. Okay. But I personally feel level 1 does the most of the work. Level 2 and level 3 is the supervisory. They sets references for inner control loops. Okay. So here I will stop. So these are the references. There are good number of references available in the literature, where you can see these things are further explained. Okay, what are the modification of these works which are done, those also are explained. I just give you the basic idea of this hierarchical control, which will help you understand the modification of this control. Okay, so now the question answer session. So online, offline participants, if you have any questions from any point, let me know. I will be happy to explain. Okay, so next from 3:45. Okay, so next session will start at 3:45, where we explain about MPPT of fuel cell. MPPT. So fuel cell basics I already discussed. The MPPT just term I mentioned. So MPPT term I mentioned. So we'll understand the MPPT control of fuel cell in next session. Okay. So if you don't have any query, then I can stop here. Okay. Thank you. Yes.
Sir, it is the same like primary, secondary, and tertiary in the grids, like the primaries, the primary governing system, secondary and tertiary, like tertiary is market based, secondary is AFC based, and primary is the voltage and frequency control. Is same like that, sir, for the microgrid?
See, philosophy could be same. The philosophy could be same. The control wise it may be different based on system parameter. Every control that depends on system parameters. As I already mentioned, here one crucial assumption is theta equals to 90 degree, not equals to, nearly 90 degree. This is one of the crucial assumption and may not be true for each and every system. Okay, as you saying in power system this assumption may be one of the best assumption that we can assume. For microgrid there could be a deviation. Okay, so philosophy could be same.
Okay, sir.
Okay, then we'll stop here. Thank you so much. So welcome back to another session. This is tutorial session 2, where we will explain about MPPT of fuel cell. So when I discussed about fuel cell, I started with saying that MPPT that we need to implement for each and every thing, like not thing, each and every like PV, wind, hydro, mini hydro, and then fuel cell also. So there the reason I told that the output power depends on, let's say if it is a solar, it depends on solar irradiance. If it is hydro power plant, it depends on water flow. If it is fuel cell, it depends on fuel flow. So here this is how we will proceed. First we'll give some introduction, then we'll explain some fuel cell modeling, and then system architecture, and then some simulation result will show how we can implement fuel cell MPPT in MATLAB. Now in fuel cell, this I already explained in my first lecture, that in fuel cell we have, this is the structure of the fuel cell where it generates electricity by injecting hydrogen, pure hydrogen from one side and oxygen from other side, where in the electrodes it splits and delivers electron to the load, and then it recombines with oxygen again and exhausts air and hot air and water vapor and heat. Okay. So in this process we generate electricity definitely. We have seen that this voltage is 1.23 volt theoretically, and it goes down to 0.7 volt, because of which we need to connect them in series in order to increase the voltage level for our practical purposes. And here also one thing I explained that day, that this power delivered by this fuel cell depends on how much is the, what is the rate of fuel flow to the fuel cell. So if we see the curve characteristics, we have seen that day, that here you can see that the voltage characteristics, voltage versus current, which is dependent on fuel flow, liter per minute, and also we can see that the power point also shifting. Okay, power is also increasing or reducing if we reduce the fuel flow. So current and voltage, both current voltage both are varying, that's why the power is also varying. So with the fuel flow rate, we need to track how much is the maximum power, and we have to extract maximum power from the fuel cell, which cannot be done by just mere of having a fuel cell. And you, the basic electrical engineering, what it says, that in order to extract maximum power from any source, what you have to do is impedance matching that you have to do. That impedance matching you cannot do alone, you have to have some power converter. So using that power converter and the fuel cell, we can extract maximum power from the fuel cell. Now from here, Rasmi Ranjan is there to explain. So from here he will explain, and he will end with this simulation. He will execute. He has executed and taken some result, and that he will explain. Over to you.
Thank you very much, sir. Good afternoon, everyone. I am Rasmi Ranjan Swain. I am currently pursuing my PhD under supervision of Professor Indrajit Sarkar and Professor Monalisa Pattnaik. Today I am going to explain the fuel cell MPPT application of fuel cell using P&O algorithm. As explained by earlier by sir, this is the, in the previous session we are described, this is the equivalent circuit of fuel cell, which helps us to dynamically, which helps us to predict the fuel cell variation or the fuel cell performance dynamically. So here are the these are the design equation of the fuel cell. Here you can see the cell voltage is defined by nurse voltage and subtracted by sum of the losses that are occurring in the various parameters. Like here in the equivalent circuit, you can see the three resistors are connected. R concentration is the concentration, it represents the concentration loss occurred in the fuel cell, and R arc represents the activation loss associated with the fuel cell, and R ohmic is the ohmic loss present in the fuel cell. Here with the help of using this equation, we can easily model the fuel cell to predict the performances. And these are the two figures associated with the fuel cell. The first figure depicts the polarization curve or voltage versus current curve of the fuel cell. Here you can see three different regions are present with this curve. First one is the activation loss region, and second one is the ohmic loss, and last one is the mass transport loss region. These losses are we have seen in the previous equivalent circuit diagram, and the right side figure represents both the current versus voltage, or the voltage versus current density, and the current density versus power. The left side y-axis represents the voltage with respect to current density, and the right side y-axis represents the power. Here you can see the maximum power occurred at around 45.02 ampere. You can trace the value from the graph, and on the same current value we are getting the voltage value of around 28.94 volt. So with this this is happening at 13 liter per minute of hydrogen flow. And this is your system architecture or the system associated with the fuel cell unit. Here you can see the fuel cell unit is connected to the DC bus by using a boost converter. The converter design is already described in the previous session. So with the design equation, we can calculate the fuel, the inductor and capacitor associated capacitor value with the associated system. And this is also explained in the previous session. There are multiple MPPT techniques are existing, such as classical MPPT method, or the intelligent or the optimization based MPPT method. There are present, but here we are focusing on the classical MPPT, or that is also called the perturb and observe MPPT algorithm. Here is the basic flow chart of the P&O algorithm. Here we first get the value of voltage and current of fuel cell unit, and after that we will calculate the power. And after calculating power, we first compare the power, that is the change in power is greater than 0 or not. If it is greater than 0, then again we compare the change in current. As in the previous session, we see that P&O also work for PV system, but there we are checking for change in voltage with respect to change in power. But with the fuel cell system, we are checking the change in current with respect to change in power. So if the change in current is greater than 0, then duty cycle is adjusted or the slightly reduced to meet the exact duty cycle. And if it is the opposite scenario, then the duty cycle will increase. Similarly, if the power change is not less than 0 or not greater than 0 or less than 0, then you also check for another scenario, that is change in current is less than 0 or not. So accordingly, the algorithm will calculate and update the duty cycle to meet the maximum power. Now coming to the simulation. Before we start the simulation, first we have to configure the model or the model parameter. Here you can see the screenshot of that model configuration parameter settings. Here three important things are there. First, simulation time, then simulation it is depending on the solver selection and the solver details. For the simulation time, you can choose it should be started from 0, and we can choose as much any time if you want. For hardware, if it is hardware real time simulation, then it can be up to infinite. But for simulation, due to lack of time, we are choosing only 2 seconds of simulation time. Here another important thing you have to keep in mind, that the solver should be in fixed step. There are two types of solver: fixed step basis and variable step. Here we are choosing fixed step, and the solver should be anyone, but for this simulation we are taking only ODE 8 and ODE 5. And after setting the solver setting, we have to check the step size. Step size we are taking here as 1 microsecond. Before going to the actual simulation, there are some overview to the components utilized in the fuel cell system. The main component of the fuel cell system is fuel cell stack. This is the path I have given that will directly go to the fuel cell. By following this path, we can directly add to this model, and after these are also some other components that are used in the modeling. And this is the actual simulation model we have to build in the MATLAB. Now we are going to MATLAB. First we have to create a new blank model, and after this after creating the model, we have to set the model configuration parameter. We can directly go there by pressing Ctrl E or by right clicking and then model configuration parameter. Here we have to give the start time and stop time. For stop time I am giving 2.5 seconds, and solver selection I am giving by default it was a variable step. We have to change it to fixed step. After selecting fixed step, this solver auto, it should be showing some various solvers. For this list we are choosing ODE 5, and after that we are going to solver details. The fixed step by default it was auto. For our simulation purpose we are setting it 1 microsecond, and click apply, then OK. Here in this slides I have shown the direct path to fuel cell stack. Let's follow the path and add fuel cell to our model. It can be found in Simscape, Electrical, then Specialized Power System. Go to the library browser, then Simscape, then Electrical and Specialized Power System. Electrical, here you can see the fuel cell stack. Right click and click on the add block to the model, or directly you can press Ctrl I by selecting the block, or you can add by directly searching here. These are different methods to add the component to the model. After adding the model, we have to set the parameters. By using the equation mentioned earlier, we can model we can model the fuel cell by using the equivalent circuit. But for the time constraint, we are using the preset model of the that was provided by MATLAB. Here we are taking the fuel cell PMA proton exchange membrane fuel cell of 1.26 kilowatt of 24 volt. Here also we can use the actual fuel cell by providing the provide the data from the manufacturing data sheet. Here you can, for that purpose we have to choose user defined, Then after that, these fields are editable. We can use whatever the parameters available with the manufacturer. For this simulation, we are using the preset model. By clicking the selecting the preset model, we have to check the parameters of the what parameters are available by selecting those model. Here you can see the polarization curve or the plot. By clicking the plot V and VI characteristic, we can see how much power it can generate. See, you can this is the nominal power this fuel cell stack can generate, but it can go up to 2 kilowatt, but this is which is not safe to operate. So for safety purpose, this fuel cell power is limited at 1.26 kilowatt. And for the now you know how much power this fuel cell will operate. Let's see other parameters associated with the fuel cell. By clicking on the fuel cell parameter, another pop-up window will open, and here you can see the stack details. The stack power, nominal power is 1.26 kilowatt or 1259 watt, and maximum power it can go up to 2000 watt. So similarly, the fuel utilization, here you can see at 15.22. This is the by default or the preset model. It can use fuel up to 15.22 standard liter per minute and air up to 36.22 standard liter per minute. To check different performance of the fuel cell, we can use this signal variation, or we can control how much fuel we want to give, or how much fuel air flow we want to provide to the fuel cell, so that we can assess the performance of the fuel cell. And for that purpose, we can go to signal variation and turn on the what parameter we need to regulate. For this simulation purpose, we are only turning on the fuel flow rate and air flow rate parameters. Now let attach it to the let's attach the converters and loads to the simulation. By using this provided path, you can directly go to this component and add it to the model, or directly you can search for the various components, such as for boost converter we need one inductor, to see the different parameters of the fuel cell. We need a bus selector, because the measurement port is the signal, multiple signals are coming across the measurement port, so we have to separate it to see what type of signal you are receiving. now the converter is complete, and to some measurement device we need to add. Measure the fuel cell voltage and current. Some voltage measurement and current measurement device is implemented before the converter. By default there are two signals which is not usable for us, so we need to delete it, and these are the signal available with the fuel cell stack voltage, stack current, efficiency, flow rate. These are the parameters available, and but we only need the voltage and current. Let's rename it is as VFC and current as IFC. And to implement MPPT, we need a function block, MATLAB function block. So where we have to write the code for the algorithm. And to provide the fuel flow and air flow rate, initially we add the two constant block, and that means we are providing constant fuel and constant air flow to the fuel cell unit. Let's give it fuel flow rate at 13 liter per minute and air at 7 liter per minute. And I have previously written the P&O MPPT algorithm code, so I will directly add to the MATLAB function. This is the code. By previous algorithm, we have seen first we have to calculate the first get the voltage and current value of the fuel cell, and then calculate it the power. Here in this block we are giving two input, one is IFC and VFC, and then current of the fuel cell and voltage of the fuel cell, and we assign it to two variables, and here in this line we are calculating it to the power, and del V or this is the if and else statement, that is the here this comparison of the assessment was done using this if and else statement in the MATLAB function. The final output of the system will function will be the duty cycle of the duty cycle at MPPT. Here we will provide the voltage and current input to this MATLAB function block. and to keep the duty cycle in range, we are using a saturation block. In the saturation block, we are giving the lower limit at 0 and upper limit at 0.9. So the output of this block should not exceed the 0, it should be limited between 0 and 0.9. And this is the duty cycle. To trigger this IGBT, we need PWM pulse. So we need a PWM converter or PWM generator. And here the switching frequency we are giving 20 kilohertz. Now the MATLAB function block, it has the update method, means at what time it will update the duty cycle. For that we need to edit the data, and the updated method in discrete, and the sample time of the updation we are giving 0.02. This sample time means at every 0.02 second this function block will update the duty cycle of the system. And at last we are adding a power GUI block, and the settings for this are simulation type discrete and sample time 1 microsecond. And to see the result, we are adding the scope and display. To check the power, we are using a multiplier. The MUX will combine the signal and send it to the single display for the viewing purpose. And to receive the parameter, we need a scope with 3 input. And voltage, current and power. The respective ports are connected to each required output. And to see the duty cycle, we also need another scope. duty cycle is tracking, or the MPPT algorithm is try to track the power flow.
That is where you kept MPPT.
The power is gradually increasing. Here we are giving the initial duty cycle at 0, so that's why it was taking so much time. If we reduce the initial duty cycle or increase the initial duty cycle, then it might go faster. Now the duty cycle is getting stable. it started tracking now. So you can see the 3-step duty cycle. So the MPPT is working. Presently the fuel cell is giving 1300 watts of at 28 or 29 volt and 45 ampere of current. If you change the fuel flow now, the power will drastically reduce. So to demonstrate that, and now the current fuel flow is at 13 liter per minute. I am reducing, and the fuel cell is giving 1300 watt of power. Now I am reducing it to 9 liter per minute, and let's see what happens. First, see the duty cycle. The algorithm detect a source variation or the fuel flow variation, and it's recalculated the duty cycle again. The duty cycle is starting to decrease. Now it is getting stable. Again it is started to tracking the maximum power point available at maximum power available at 9 liter per minute, which is around 1 kilowatt. So 200 watt of power getting reduced by reducing the fuel flow. This is also works with the source. This is working with the source change. It is also working with the load change. If the load changes and suddenly or gradually, then it is also able to track that change. To demonstrate that one, I already designed another model in which I have given some timing, some predefined time limit. So where like fuel cell, like fuel flow and load change timing, and also some variable load configuration. Here in this model, we are giving simulation time is same 2.5 seconds. From 0 to 1 second, we are giving 13 liter per minute, and after 1 second, the fuel flow became 7 liter per minute. And accordingly, similarly for the variable load setup, we are using two load in parallel combination. The first load will last till 0 to 2 seconds, and the second load is will turn on at 1.5 seconds and last up to 4 seconds. But our simulation will stop at 2.5 seconds. So let's make it 2.5. Here the load is around 2 ohm and 2.8 ohm. So first load will last till 0 to 2 seconds, and in between another load is turned on and at 1.5 seconds, and it will last till 0 till end of the simulation. So all other parameters are same. So let's try to run this setup and see the results, what will happen. The power starting to increase. And here the initial duty cycle is also starting from 0. So I will reduce that. Now it is reached the MPP at 13 liter per minute and only one load is operational. So the load is taking around 1270 watt and the source is generating 1300, almost 1300, 1.3 kilowatt, and the rest are getting lost in the system. So you can also see the power, voltage, current and power graph of the MPPT. The power is almost getting, average power we are getting here as 1250 to 1260 watt. And the load will, source will reduce to at 1 second from 13 liter per minute to 7 liter per minute. The loads fuel flow to the system getting reduced, so the power available at that instant will also reduce from 1300 watt to almost it will get stable at 950 or 900 watt. The duty cycle is also recalculated by the algorithm. Now it is getting stable at around 900 watt or 850 watt, and at 1.5 second another load will be added to the system, so the overall load of the system will increase. So let's see if that algorithm will try to track it. It is getting 3-step waveform, that means MPPT is working fine. another load was added. So there is a drop in voltage and drop in power also. The algorithm will try to track the maximum power point again. Now it is stable at 0.07. And the power is also working at given at maximum power point. Maximum power available at the system is around 850 watt, and the system is consuming 820 watt of power. At at 2 seconds the load will disconnect, so that will again try to track that changes. That is detected by the algorithm, and the algorithm again try to recalculate the stable duty point. Each point is updated at 0.02 seconds. So the algorithm perturb at each 0.02 seconds and observe for the change. If any change is detected, then it try the perturbation again and again try to observe. So that's why the name is perturb and observe. The power is almost MPP at maximum. We are getting the 3-step waveform for the duty cycle, so MPPT is also working here. So we are tested the source change and load change, both scenario with this MPPT algorithm. these are the results I have shown. The green color shows the steady state MPPT performance, and at 1 second we seen source change happening, and that the fuel flow changes from fuel flow getting reduced, and this is the voltage waveform of the fuel cell. We are seeing here the voltage is almost constant because it is a voltage source device, and this is the power waveform of the fuel cell. We have seen this graph earlier. Here there is a source change and these two are load change. Here the load is increased, means another load is added to the system. At this change denotes one load shedding, that is one load is removed from the system. And this is the associated duty cycle tracking of the fuel cell. And these are the references. Thank you. Now, if you have any question. If no, then we'll stop here.
Hello. Thank you, Rashmi, for your nice presentation. I was watching this on YouTube. Okay, and then I have seen how nicely you presented. So just one comment I want to add here. Like as I started with saying that only fuel cell will not do. We have to add something which is a converter, power converter. The power converter that is added here is the boost converter, right? So I personally feel the boost converter is one of the best suited for this MPPT tracking for this DC-DC converter, because as I told you, the ripple content to the source should be minimum. Okay, so since a boost converter is having an inductor at the input, so it reduces the ripple current. Contrary to buck converter, where you will see that the source current is discontinuous in nature. So here it is continuous in nature, continuous with some ripple. So this is best suited, and also it's this kind of thing has low voltage, so always you have to boost the voltage. So boost converter works fine with this. Okay, so with this we will close the session, and also we will close for today, because this was the last session. So we'll start tomorrow. Tomorrow I think at 10:30, right? So tomorrow we'll start with 10:30 with C2000 microcontroller demonstration we'll have. Okay. Thank you everyone. Thank you for attending today's sessions. Thank you.